So good morning. We are here. I'm running the connection with my cell phone. In the meantime, while the technician comes to fix the problem we are facing with the Wi-Fi, I don't know if our colleagues from China are there. So first of all, I would like to apologize with you for the delay today in the connection. Fortunately, we are facing some problems here. The first problem is that unfortunately, Professor Ruffini didn't feel very well yesterday afternoon, and so he had to go to the hospital. So they are making some tests today. So we hope so he's under observation now, and we will know something more about midday. Hopefully we will know something. I talked to him. He feels good. He feels better, and of course he sends his greetings to all of you. And we hope to have him here with us very soon. We hope today or at most tomorrow. So let's see if he can even connect with us during the day today. So let's see if at some point of the morning or the afternoon he connect directly from there, from the hospital. But the good news is that he feels good now. He's just waiting for some results of the test. So this is the current situation now. We will run the meeting here from Villarati while we wait for Professor Ruffini. So we are here with Narek Sahakyan is here with me.
Hi everyone.
The director from ICANNET Armenia. So maybe if I don't know how to proceed, should we?
Maybe we wait like 10 minutes.
Yes, we'll check the program now. Maybe I will share the program on my screen. People from Pescara, maybe you can answer some last minute changes or whatever. So I would like to share the latest version. So Elizabeth or Gabriel, if you send me the latest version, I can share my screen with that program. Good morning, Professor Treves.
Good morning.
Welcome.
Thank you. I am really anxious to hear about Remo.
Yes, so you know, Professor, that he's in the hospital now.
Yes, I was hearing what you said a moment ago.
Yes, but he feels okay.
Okay, probably he is overstressed. I understand that.
Yes, we talked to him a few minutes ago. He feels really good now. So just that you know how it's in the hospital. I mean, they have to make checks to be sure that everything is fine.
Of course, now,
yes.
of course, we are in the COVID season, so we will be extra careful.
Yes, yes. So we are. I'm just waiting for this latest version of the program because I think to know the list of our colleagues that are going to speak now. So I'm waiting for the program from Pescara.
Remo was mentioning that I am scheduled at the time.
Okay, so okay, let's see. They just told me that the program is updated in here on Indie Core platform, so I will download it now.
Yes.
Oh, it's live now. Okay. So you can. Works. Yes. Okay. Good. Timetable.
Did you share your screen or did you not see your screen?
Yes, I will share my screen now. For the moment, just to okay, here is. Okay, so do you see my screen now?
Oh, yes, timetable. Yes.
Okay, I will just close a few things here.
Yes.
So now I asked to or colleagues from China if they are there. Are you around, Professor Yun Long?
Hi, I'm here.
Hello, good morning.
Good morning.
Welcome.
Sorry to hear the news.
I'm so sorry for this. I mean, you know, these are unpredictable issues. We will try to do our best anyway and run the program as scheduled while we wait for from Professor Ruffini. So I think we need some chairman from your side. I think it's you for this connection with you. I have here this list. Let's see if you are all around. So here we have this congratulatory letter from Bao Xinhe, from Professor Bao Xinhe. We have also Ye-Fei, Yifu Cai, Zigao Dai, and Xiqian Shen. I don't know if we have all of you are connected.
I checked and I found President Bao is not here yet.
Okay, so but in the meantime, I think we can maybe start, and bit by bit that they get connected. Who is present?
Good morning, everyone. Yes, here's Pescara, Jorge. Morning.
Good morning, Gregory.
Yes, so we have the chairperson, Yun Long Zheng.
Yes.
And do you have the program in hand? We have the.
It's shared on the screen. I have what you see on the screen.
Okay, great. Yes. Do you have any connection from China? We have Ye-Fei.
Hi, Gregory.
Yes, hello.
Yeah.
Good morning. Who else is connected? Let's check. Because if we can start with the program.
Yeah, so
Can you please identify the speakers?
Mm-mm.
Maybe we start with no, Yuan, no.
So there is a letter to be read. What is
The first item is congratulation letter of active Professor Remo Ruffini.
Yes, congratulatory letter. Who is going to read this letter?
Is Professor Zhao connected?
So shall we start? And now the situation is Professor Bao Xinhe seems not here, but Ye-Fei Yuan and Professor Yifu Cai is here. So shall we start with Professor Yuan?
Yes, the second one.
But do we have a letter? We can just project the letter on the screen, probably.
Yes, Gregory, as a contribution for President Xinhe Bao, we have the letter that UST
should I have
congratulate for Professor.
Okay, probably.
in the
Yes, probably. Jorge, if you are showing the screen, maybe you can show the screen. This way we can share the letter with everyone.
Where is the letter?
Elizabeth, can you help us?
Your screen now, and you read the letter.
Okay, I'm looking for the letters.
Yes.
Okay, I got it.
Okay, did you find it? Otherwise, I will share the screen.
No, you share your screen.
Okay. Okay, I will share the screen. You have to stop yours.
Yes.
Okay.
Okay, I stop mine.
Okay, here it is, the letter that we received from the president of USTC. And it's a congratulatory letter for Professor Ruffini's 80th birthday. And so I don't know if the chairman will read the letter.
Elon, can you please read the letter?
Okay. Yeah, okay. Dear Professor Ruffini, greetings from the University of Science and Technology of China. I'm greatly pleased to know that you will celebrate your 80th birthday on May 17, 2022. On behalf of USTC and myself in person, I could like to extend our warm congratulations, heartfelt appreciation, and best regards to you upon this special date. Dated back to your 17th birthday in 1979, you struggled your trip to China despite the numerous difficulties and paid the visit to USTC. Shortly after China's reform and opening up, that is an important milestone in the historical progress of international exchanges and cooperation at the USTC. We are gratitude of your selfless contribution to the development of astronomy at the USTC over the past 43 years, especially from the perspective of talent training in the field of relativistic astrophysics. In 2021, I am very happy to establish the agreement on scientific cooperation between International Center for Relativistic Astrophysics Network and the USTC with you. USTC wishes to work with ICALET to continuously enhance our cooperation with more productive achievements in the near future. It is our sincere hope to welcome you to visit USTC again at any your convenient time when restrictions upon international travel is alleviated. Our best wishes to you for happy, peaceful, and healthy birthday. Bao Xinhe, President of USTC. Happy birthday.
Thank you. Thank you. Thank you very much for reading this very nice letter from the president of USTC. Thank you very much. So,
I had something that I wanted to present for Remo Ruffini. It would take about 10 minutes or so. Is there time for that? Also, how do we arrange? I want to actually show it. Should I send it to the Ikranet thing and you could then show it there?
Hello, Professor Qadir. I think, but I think you were scheduled for tomorrow morning. If is today?
He was moved, Jorge, according to the.
It was moved.
So
Okay.
is the update.
Okay, so we'll. Okay, Professor Qadir. So we will just follow the program. I don't know today. Yes, it will have the time for that. So if we follow the program, next is Professor Ye-Fei Yuan, I guess.
Yes. First, let me introduce the speaker. Professor Ye-Fei Yuan is from University of Science and Technology of China. Her research interests include relativistic and high-energy astrophysics. Today, he will talk about pulsar timing and binary black holes. Let's warmly welcome. Professor Yuan, are you there? Oh, it seems there is a breakdown.
Yes, they were mentioning in the chat, that they have some problem with the connection at the USTC now. Let's see if they manage to share. Professor Ye-Fei, are you there? But it seems that he's a connection is unstable. Okay, so he can hear us, but we can hear you, Professor Ye-Fei. We don't hear you. Maybe we can try another connection. Maybe
Yes, probably we can move to the next speaker, and then if Professor Ye-Fei connects, we have him later on.
Who's next in the list? Professor,
we have Yifu Cai. Yes. Can we ask him to speak? Yifu Cai, can you hear us? Yifu, can you hear us?
No, we will go. Okay. So Yifu Cai also is facing problems with the connection. He says probably with the USTC firewall. Let's see, in the meantime, if they fix that, we can maybe go ahead with the program. Who's next? Zigao Dai. Do we have Zigao Dai with us? No, it seems he's not around. Or Xiqian Shen.
Hello? Hello? Hi. Hey, George, can you hear me?
Hey. Hey. Yes, we can hear you.
Yeah,
You are in the gym.
our director, Professor Shen Zhiqiang is not right. He is not available now because he's working on, for his responsibility for the COVID-19 control in our observatory. So he's a director, so he is very busy for that. So maybe I can, say something words, actually, we present our best, our warmest greetings to the birthday of 80th birthday of the Professor Ruffini. And okay. And I think I can show some pictures which have some connection between the, Professor Ruffini and the Shanghai Astronomical Observatory.
Yes, so
can I share my screen?
Yes.
Okay, good, great. Okay, I think now you guys can see this screen.
Yes, we see it.
Yes, I can share. So we have warmest greetings to Professor Ruffini. Okay, sorry. Okay, actually that I think that the very important event for the collaboration and connection between equalate, of course, Professor Ruffini with Shanghai Astronomical Observatory is, I think, the very important time point is 2009, about 13 years ago. We have the first Galileo Xu Guangqi meeting in Shanghai. I guess a lot of, maybe some of you are attended this meeting. Okay, and here this is the picture that I think taken in Shanghai, and this is Professor Ruffini, and this is Professor Jin Yipeng, which is a professor in Shanghai Astronomical Observatory before. I think I see a lot of other people here. And we have have a memory with for the Xu Guangqi and Maglich in the very beautiful small park in front of our observatory. And you can see here is this is Professor Ruffini, and this is former director of the Shanghai Astronomical Observatory. Okay, and this session, and this is Jorge Rueda. Okay, and this is a very nice picture I took 13 years ago. 30 years ago, I took this picture for Professor Ruffini and Professor our former director of show of the Shanghai Astronomy Observatory, and in front of the statue of the Xu Guangqi. And I think this picture is very similar to this one, which is Xu Guangqi. We discuss something, maybe science, maybe the religion of from the Western with the Italian, very famous Italian Matrix, and they have a bridge to. They build a bridge to connect the Western and the very ancient China. Okay, a few hundred years ago, and in that time, and Professor Ruffini and our former director also stand before the statue of the Xu Guangqi, and I think these two pictures is very similar, and it's something consistent. It's you can see here, and we have a lot of anyway. Okay, so also in about 5 years ago, we have agreement before between the Shanghai Astronomical Observatory and Ecolet, and we signed this agreement behind in front of the government of Italy and China. Okay, so you can see here, we stand here, and we have this China-Italian Science, Technology, and Innovation Week. And okay, anyway, that we have very, we have warmest greetings to Professor Ruffini's 18th birthday. Okay, thank you. Thanks. Thank you.
Thank you. Thank you.
Thank you, Wenbiao. Thank you very much for recalling us for this. Remember this first meeting. Actually, I was there. Was a fantastic occasion to meet you. I think that was the first time that we met together. We too. So it was very pleasant to see that.
Okay, nice.
Thank you very much.
Okay, thank you. Mm-hmm.
So in the meantime, right here we have here our colleagues from Germany. So so we start to fill up the room here. So Professor Rashid Sunayev is here. So we can continue. So thank you again. So who, I don't know if the people from USDC, if they managed to fix the problem. If it's not fixed yet, then you can go ahead. Maybe the people from Pescara, they can. Gregory, you know who's next now?
Let me see. The list here is Pascal Cardonet. So I'm sorry that the speakers from China have the big problem to share the screen, and so maybe we should move to the second session. Sorry again.
Okay, so let me try to check the people. Gregory.
Yes, I am. Yes.
Gregory, can you please confirm the program now, because I'm not sure that what I have here is the updated program.
Yeah, the updated program is in Indico, so we have the chairperson Pascal Chardonnay, and the speakers are, the first speaker is Professor Aldo Treves, who is here. Then we follow with Asghar Qadir, Tsvi Piran, Jorge, yourself. Then we have coffee break. Then Narek Sahakyan, Rahim Moradi, and Professor Bisin Chen. This is the program. Do we have Pascal joining us?
No, I don't see Pascal is connected, and he's not here in person. So, but anyway, any one of us can share the session, I think. No.
Yes, no problem. Since you are speaking, I can share the session.
Yes, I mean you can do it if you like, Gregory.
Yes, okay, I can
because
do that.
I have to speak and Narek have to speak, so
sure.
It's better that you do. Okay.
Sure. If Pascal by chance arrives, we will switch to him. But in the meantime.
Sure.
Well, we have 3 more minutes. Maybe we wait just to.
Yes. So Professor Treves is already there, is ready.
Yes.
So as at 9 in just 3 minutes we go. Okay.
Great. Okay. And we have any news from Professor Piran?
No, I don't have any news from him. I suppose he will be connected.
Connect later. Yeah.
Gregory.
Yes.
So here we have all the people now. I mean, just arrived Professor Piran and Professor Nathalie Deruel, and we have also Professor Lamensal, Professor Schneider, all of them here in the room.
Very good. We have, however, some delay with the signal.
I confirm you that they're all here.
Okay, very good. But we have some.
Oh yes, you know, I'm running the connection with my cell phone. You know, we have a problem with internet. I actually don't know if it will resist for the entire session, you know, because I have a limited connection.
Okay.
But anyway, we try.
Okay, they are going to fix apparently the connection soon, but maybe in the meantime, let's hope your connection works.
Yes, we are waiting for the technician that should show up at any moment here to fix the problem of the internet connection.
Okay, so if Professor Chardonnay arrives, maybe we can ask him to chair the session.
Okay.
He doesn't mind, okay? Pascal, can you hear us? Hello, Pascal. Professor Chardonnay. Jorge, please ask him to join the meeting. Because we must start.
I don't see Pascal actually.
Okay, let's start the session then, and I will chair the session unless we have Pascal joining us, okay?
Okay.
So good morning, everyone. We are here at the meeting celebrating Professor Remo Ruffini's birthday, 80th birthday, and we now can start the morning session. And we have our first speaker, Professor Aldo Treves, who will recall the early years of Professor Ruffini's career. Professor Treves, please, you can start.
Okay, good morning, everybody. I am a little embarrassed because I understand that Remo is not with us. I'm not sure if he's hearing us or not, but doesn't matter. I met Remo for the first time. Can you hear me?
Yes, we can hear very well.
in 1967, at a workshop in Bologna, he had graduated since a few months, and I was graduating in Milan. And I went through the list of the speakers, of the participants of this meeting, and I think that my interaction with Remo overdates all the participants. My interaction with Remo was immediately positive, and one of the reasons is that he had graduated with Cattaneo and Amaldi in Rome, and I was graduating with Occhialini in Milan. And Amaldi and Occhialini were the fathers of physics in Italy at that time. I'm mentioning that because I'm convinced that Remo was really very close to Amaldi and also to Occhialini. To Amaldi, it is well known because Amaldi has this fixed idea in 1967 about gravitational waves, and he was enthusiastic to have a young person like Remo working on general relativity. The interaction with Occhialini was a little less straightforward. It was through Occhialini's associates. I remember that Remo, later in his career, when he was professor in Rome, made an effort to have two of these former students of Occhialini in Rome. But probably the most important was the association of Remo with Giacconi. That was a friendship between Remo and Giacconi, which lasted for all the life of Giacconi. And Giacconi was a former, not a student, a former associate of Occhialini. But let us go to the meeting in Bologna. That was in 1967, and it was for graduate students or young graduates. And it was about the new astronomy. What in 1967 was the new astronomy? It was radio astronomy and the newly born X-ray astronomy. I was very impressed by Remo Ruffini because he was speaking of something really exotic about neutron stars, black holes in 1967. And my impression is that all the audience really didn't know what he was speaking about. But it was very interesting. He was really a theoretician. He made the thesis as a theoretician in Rome, but he was extremely interested in the observations. So it was very nice to have a contact with him. The next time I met Remo was in 1968, and that was at the Brandeis Summer School. Between 67 and 68, the situation had changed drastically. Because in 68, pulsars were discovered. The Brandeis School was on relativistic astrophysics, and it was very theoretical. I remember it was the first time I went to the US, and I was very intimidated. I was meeting people whom I knew by fame, but have never seen really. Also, the school was extremely theoretical. the novelty of the pulsar discovery made a complete change. Remo was there and he was completely at his ease. He was finishing his first postdoc year in Princeton, was enthusiastic about his interaction with John Wheeler, and was finishing a paper with Bonazzola about what we now call boson stars. It is a very well-known paper. And that was very interesting, because if you go through the list of the participants to the Brandeis School in '68, you will see that many of the protagonists of relativistic astrophysics in the following years were just there. And it was a contact between mathematicians, really, and astronomers, with probably the first contact. Remo was certainly trying to produce a group of his own in Princeton. And then it initiated perhaps one of the most productive periods of Remo careers. That is at the end of the 60s, beginning of the 70s, and he made an incredible effort on various themes. Certainly he was interested in neutron stars. In fact, the pulsar discovery made neutron stars one of the main subjects. And I would like to recall the paper he produced with Rhodes on the maximum mass of neutron stars, which was generated essentially at that epoch, even if it was published somewhat later. And especially there is the period of collaboration and contribution with Wheeler, with this idea of ergosphere, the famous paper in Physics Today for the introduction of a black hole, and the concept of irreducible mass with Christodoulou, who was a student of him, the idea of considering irreducible mass also for charged black holes. So it was very important, as I will mention later. And you see, it was very impressive to see how much he was producing in a very short time. And all these products, in a way, were presented at a very important meeting, which was the Lesouche School of 1972. Now, Remo was already a very authoritative person in the field of black holes, was, of course, participating to the school as a professor. I would say that at the Lesouche School, there was the creme of the black hole physics at the time. What had happened in those 3 years from the astrophysical side? Something very important. With the launch of Uhuru, the satellite which was led by Giacconi, X-ray astronomy arrived to a maturity stage. And one of the first products was not the discovery, but the discovery that followed, that one of the best known X-ray source, Cygnus X1, was most probably a black hole. And that was really extremely important. And I think that Remo was one of the first person from the GR side, so the side of a theoretician, to understand the importance of a discovery and to work with the astronomers in a way. At the time I was at MIT, and we invited him. I'm sorry, I hope he is hearing us. We invited him to give a seminar at MIT. There was a very strong group of X-ray astronomy, and my colleagues were, you see, I said, but after this is a person, a theoretician with whom we can speak, we can have a direct link with. And that was impressive, important and impressive. I would like to recall also one of the contributions he made at the Blazars meeting. That was something we had done together, and was about charged rotating neutron stars. It was a very simple exercise. Now, after 50 years, 54 years, I think it was very naive. The idea was simple. We were all excited by pulsar electrodynamics. We considered and reconsidered the classical paper of Deutsch, the paper of Goldreich and Julian, and asked ourselves, what would happen if the rotating magnet is charged? And the question was, how would the electromagnetic energy be changed? And we considered only the external energy, so it was extremely naive. And the result was, it is quite obvious, that the external energy diminishes if there is a charge. There was no astrophysical application to that computation, but what I would like to remind is that Remo had an adamant faith that that was important, and there should be a generalization of our calculation in the case of black holes. I think that this idea was one of the fil rouge of Remo ideas about black holes for all his career, for 50 years or so on. And of course, there were some generalization, very important paper of Wald on this line. And if we go through Remo's numerous papers, especially all the papers about gamma ray bursts, we see that this idea is continuing. I am mentioning probably one of his last paper, the one with Rueda and Kerr, and that is, there is something back from his idea of importance of charging the black hole. my relation with Remo has been one of real friendship. I always considered him as a major colleague. He is my senior by some 3 years, but he has always been much younger than me. He's young in his enthusiasm, in his capacity of transferring enthusiasm to young people. So I'm here to end this short talk just saying, best wishes, young Remo. That's it.
Thank you very much, Professor Treves. This is really a very nice recollection of the early career of Professor Ruffini. Very vivid recollection. Thank you. Thank you so much. I think we have no time for questions now, and probably we can postpone the question to the coffee break time. And we have the next speaker is Asghar Qadir from Pakistan. Asghar, can you please start? Professor Qadir, can you hear us?
Did you say my name?
Yes, yes, we can see you. Yes.
But then I was supposed to be tomorrow.
We have you in the program today.
Tuesday, May the 17th, 9:15 to 9:30.
Check. No, Tuesday, no, Tuesday morning session is different. Is the one with the people in Nice.
Well, I can come in if, can I get the sharing screen, and then I'll be able to.
Yes, you
present
can share your screen, please.
Okay, so I'll prepare it right now to get these. I have to, as yet I'm not seeing how I put my own screen on there. Just one moment and I'll come back.
In case you like, we can share.
I thought it was for tomorrow. I'll just get my talk out. And
okay, you actually sent us your presentation. If you like, we can project your presentation from local computer.
Yeah,
is okay.
I thought it was for tomorrow and not today. I hadn't got it out as yet. So I'll just get it out and then proceed. Yeah. And now back here. Okay, this I need the full screen, and then I need to be able to. Are you seeing me here?
We can see you, but we cannot see your screen yet.
I need share screen.
Share screen, yes, on the bottom.
Yes.
You should see the green button.
Okay.
Now it should be okay.
Yes, we can see. Thank you.
Okay, I'll try to quickly go for everything now. So this is a suggestion for possible test of the Ruffini-Argel's Rueda model using the microwave background. Talked about the dark matter problem, the central black holes, the model itself, the core properties in that model. My point that there's no direct evidence for the model, and then a suggested test for the model with the hybrid core baryon model and critical core and baryon matter mass. Final quick conclusion. So the RAR model proposes a solution of two of the major important problems in astrophysics and cosmology. One is dark matter, and the other, how supermassive black holes could form so early. We suggest a test for the model using the CMB. The idea is that some of the baryonic matter will fall in the degenerate core and may form a black hole inside. This would leave an imprint on the CMB if it happens sufficiently early. The matter which we see in the universe is normal baryonic matter. As everybody knows, about 5% appears to be in normal matter, and there's 25% in dark matter. The problem is that the standard model of particle physics does not give any particle that could be responsible for the dark matter. Various supersymmetric and other particles have been proposed as candidates for the dark matter, but none has been observed. Almost every galaxy hosts a supermassive black hole at its center. Our own 4 million solar masses, its GRA star, and there are between millions to billions of solar mass black holes, supermassive black holes. The interesting thing that as early as 670 mega years, there's a 1.6 billion solar masses that has been seen. And that is remarkable that one should be able to get one that size that early. The problem with the early formation of supermassive black holes is that it is not possible to get black holes this massive through the normal mechanism of black hole formation and with coalescence. So black holes formed from population 3 stars with masses between 10 and 100 could not be expected to be to form till about 100 million years, and no intermediate black hole with mass between 100 and 1,000 solar masses has been seen. For such black holes, even 13 billion years are not enough to become supermassive by either accretion or coalescing. Nor is there enough time for black holes to form by stellar collapse and coalesce. The RAR model proposed a solution to both problems by postulating neutral fermions that could be taken to be sterile neutrinos, called neutralinos, or about 50 to 350 keV as the dark matter particles. The sterile neutrinos are weakly interacting, but do not lie in any of the 3 generations. The model assumes a self-gravitating system of fermions, which are called ENOs in the paper, or dark ENOs, in thermodynamic equilibrium and spherical symmetry, obeying quantum statistics. It explains the dark matter distribution in galaxies with central complex quantum degenerate cores. For more compact cores that could possibly explain the central black holes with finite galaxy size, energy cutoff is introduced in the phase space distribution. The phase space density of dark matter follows the Fermi-Dirac statistics with and without the cutoff effects as considered for the density profiles. So with this, solving the system of equilibrium equations of the model, different core properties for different particle masses have been obtained. And using these values, we can check whether the the core is compact enough to collapse into a black hole or not. The variation of the densities, the degeneracy parameter, and rotation curves for different masses are provided in the paper. It shows the three regions: the quantum core, the transition region, and the classical halo. So there is this so the rotation curves in the halo region tend to follow a constant behavior for which R is indicated in the presence of dark matter. Thus, the RAR model provides a very reasonable explanation for both problems. For more compact cores that could explain this thing, solving the system of equilibrium equations of the model, different core properties for different particle masses are obtained. Using these values, we can check whether the core is compact enough to collapse into a black hole or not. The variation of the densities, degeneracy parameter, and rotation curves provided there. Right, sorry. Thus, the RAR model provides the reasonable explanation, and different core properties are given in the tables. So here is the table, and you see over here the black hole, the short shield radius coming in, and the core radius, and there's the critical mass for it to form, the degeneracy parameter, and the core radius, core density are given. That's going from 48 to 345 keV max. Now going the same way with the cutoff effects, one sees the modification. You see considerably larger short shield radius coming up, and similarly the core radius has gone down. So though the RAR model provides an explanation, there's a problem of getting evidence for it. It is not possible to get direct evidence of the fermions responsible because they would be weakly interacting. Since the INOs are not in the standard model, we cannot even predict any weak interaction effect for them. A prediction that could be tested is needed. Initially, there will be this, sorry, I'll just try to move this. You could have that if the universe cools to about 3 Kelvin, the inner distribution will be squashed out of the maximum. Below the Fermi temperature, the cores will become degenerate, forming a gravitational well, and the normal matter will start falling into the well, so the fluid will not remain homogeneous. This normal matter will interact with the CMB, and the density difference inside and outside the well will leave an imprint in the CMB. We suggest looking for this imprint. Dark matter's cores for masses in the given range do not, and there'll be partially degenerate outside them. However, normal matter outside the core that falls into the well may collapse inside the core to form a black hole. We can determine the respective critical masses for cores by this formula with the degeneracy parameter there, the Planck mass, and the mass of the particle. And here we have the corresponding black hole possible formation with the baryonic matter. So for the hybrid core baryon model, after the degenerate collapse into a black hole due to the normal star falling in, the nature of the imprint would change. After the surface of last scattering, there will be no new imprints that can be left on the CMB. We suggest looking for these imprints in the CMB. For comparison, we propose looking for the imprints in the CMB that normal matter for supermassive black holes, which would form by about a giga-year, would leave, and looking for significant differences between the two, if any. So this is the suggestion, and just the caution, it is worth noting that this hybrid model is not claiming to provide the missing baryon problem, because the mass of the black holes in this model is mainly in the inodes, while the normal view would have put more baryons there. So we are not claiming that this would be able to solve anything in the nature of the missing baryons. One may worry that the imprint may be swamped by the 10 to the -5 CMB anisotropy. On the other hand, if it is of the same magnitude that is explained by inflation, considering that there's no candidate inflaton, it would be interesting to see if the core imprint could provide an alternative explanation to inflation. And so in that sense, be some sort of a test of the IRR model. To test this conjecture, one would further need to see if it reproduces the observed power spectrum. Thank you.
Okay, thank you, Professor Qadir. Maybe we can take with one short question, since this is scientific talk. And anybody has a question, please either write in chat or you can ask directly.
Could I ask a question?
Yes, please.
It's Alexander Zakharov. Hi, Asghar. I was enjoying your talk. It was really very nice. I also like this RAR model, but you did not mention, let us say, Event Horizon Telescope results and this model about, let us say, what about connection? Because Event Horizon Telescope people are saying they are seeing shadow for Sagittarius A, and also they are seeing synchrotron radiation from this region. In this case, you have to have some baryonic matter electrons or something like this. Could you say something about this? Thank you.
I didn't think, for my purpose, I'm just taking the RAR model as it is. So I'm not saying what else would I say. If the suggestion of dark matter provided by Ruffini, Argelis, and Rueda is to be taken to be the correct one, we still need to check it. And I'm suggesting how we could check it by the CMB. I certainly don't say that that has to be the correct one, because one does need evidence. As yet there isn't. But it does provide the explanation of two problems which are totally separate, apparently, and yet they're very, very important. Getting these very early supermassive black holes, one really needs to work to be able to get something like that. And an alternative explanation to the usual baryonic formed black holes is needed. Otherwise, it just can't happen that early. You can't get such large supermassive black holes in 670 million years.
Thank you. Thank you.
Okay, thank you very much for this explanation. Thank you very much, Professor Qadir. We actually have more talk on this topic later on in the program, therefore stay tuned. I think we must move to the next speaker, and the next speaker is Professor Tsvi Piran.
Yes, Gregory, we are here with Professor Piran.
Yes.
We will try to connect him now. Let me think how to do this, because I'm worried that if he connects with to my cell phone, it will slow the connection. But let's try, okay?
Let's check, yes.
And it's Android ID, if you can see it. Android, yes, it's Ye-Fei RH 723114. It works.
So I have to join the Zoom now?
Yes, you have to. So he's joining the Zoom now. He will share his screen directly from his PC, okay?
Okay, or in this case, maybe you can switch off the microphone temporarily just to not have echoes.
Can you hear me? Oh.
Yes, we can see your presentation. We can hear you. Please, you can start.
I think you can see me and can hear me, right?
Yes, yes, we can see and hear you.
Yeah, I was specially invited. Oh, you don't have to. Okay, so I will see. Next chair. Okay. Good morning. Very happy and excited to be here for this meeting in honor of Remo. And I have met Remo for the first time in 75. Oops, it is not, why did it not move? Oh, I have a problem here. Sorry. Stop share.
Screen,
Oh, you see you on the screen. You see me on the screen, but I want you to see the presentation. The presentation. Okay, so let's try it one more time. And now Zoom. Share screen.
We don't hear him through the microphone.
There was an echo.
Okay, yeah. Okay, so I believe you see the screen now. And I first met Remo in '75 when he organized this meeting on astrophysics of neutron star and black holes. This was '75, which is by now the title Astrophysics of Neutron Star and Black Hole will be very typical for for a conference, and this is standard. In '75 it was not so typical, and it was in Varena. It was on Lago di Como. I still remember the voice of the people on the ferry that was crossing Lago di Como. So and the participation was amazing. The speakers that Remo organized, everybody from Chandrasekhar to not Rael, well, we have the list, yeah, Giaconi and well, everybody was there. Everybody was there, both the old generation and old. I mean, for me, I was considering when I was young, but the old generation was 30 years old. Yeah, so all the old generation and the younger people who are now old were there, and it was really a dramatic. For me, it was a dramatic meeting, which influenced me a lot. And since then, since '75, I continue to meet Remo regularly in various places, mostly in the Marcel Grossman meetings, and in which we even organized one together in Jerusalem in '98. And of course, the most famous one, the one in China in '82, which was a dramatic event with all the efforts to allow Israeli participants to participate. So it was a long time, almost 50 years, not as much as Aldo was before me mentioned, but it's a long and impressive time that we have met. And I'm looking forward for some future meetings like this. So with this, I want to go to the topic of this discussion, which is some basic facts. So this is the outlook. First, I'll mention some basic facts on gamma ray bursts. Then I'll talk about jet propagations in stars. You will understand why this follows from these basic facts. Then long GRBs, low luminosity GRBs, direct relationship with supernova. And if I have time, I'll say a few words on GRB 17 or 817. So some basic facts and their implication, and they are all well known. And they were actually known almost from the beginning, but things could have been slightly different. We've reached these conclusions much earlier. First, the energy. Once you realize that they're cosmological, then the energy of 10 to the 50 to even 10 to the 54 ergs as a tropic equivalence implies that you must be dealing with compact objects. Nothing else can produce so much energy on such a short time. When you look at the upper limit of 10 to the 54 ergs, you immediately realize that it cannot be isotropic. There must be a beam. There is no way to produce so much energy uniformly, or unless you go to some extreme situations that I don't like. So the natural thing is being. The next set of arguments are very old. They go to the issue of compactness, that if you have 10 to the 5th so much energy and the spectrum is non-thermal, then you immediately see that the optical depth for Pair production is this F is a factor of order of 0.001. It's not F of E times H divided by omega, but it's F times E divided by H bar omega, where H bar ni is the typical frequency of a photon, and E is the total energy. And this give you the optical depth, and it is if R is the size of the compact object, this is much larger than 1. You cannot get this energy out directly from the source. Something must be happening. So
And what are the hypotheses behind this?
This is there is no hypothesis. You're just counting the number of photons that you see, and you calculate their density, and you calculate that the cross section for pair production is this is the cross section, more or less the cross section for pair production. So you see that if everything is produced on a compact object, then near in the vicinity of the compact object, the optical depth will be huge. And if the optical depth is huge, you don't get a non-thermal spectrum. So this doesn't work. It's a very old argument. So you cannot get the radiation out directly from the source.
So this is why you are adding 10 seconds.
The
Next step you are going to add.
So similarly, if you take 10 seconds, which is typical duration, and you instead say, well, R is not the size of the compact object, but something larger of the order of the crossing time corresponding to 10 seconds, you still get something much larger than 1. Therefore, you're forced to conclude that you must have relativistic motion. And if you have relativistic motion, you get to this picture here, that there is a compact object, but the compact object is producing a jet, and the jet is getting the energy out at very large distance from the source, and you get short time scale because of relativistic effects. And the major problems of energetic time scales and spectrum is solved. So this is some basic fact that underlies what is going on here. But there is immediate implication for this. And this immediate implication arises from the fact that long GRBs are associated with supernova. And this is the first case, 98 VW. It is not such a good case because it's not a typical long GRB. But this is the second case, 030329, which was a regular GRB. And there was a supernova associated with the event. And if there is a supernova, then you have to add to the picture that I drew before of a compact object and a jet, a star that's around it. And this means one thing, that the next step is to understand how the jet goes through the star. This gives us a very interesting physical question that we must answer. How does a jet, relativistic jet, go through a star, and what are the implications of that? So this is... The star do not collapse yet. The envelope of the star did not have chance to collapse. The center of the star collapsed to a black hole or to a neutron star, but the envelope, it will take hours for the envelope to react. The jet is created in the center. The jet is exactly. Yeah. And then we have to start how a jet goes through this envelope. And it's very simple. You have to drill. Just like drilling, you have to invest energy in this drilling. And only once you finish drilling, the jet gets out, and then you get all the action of the gamma ray burst and the afterglow, but only after you finish drilling. So you have to understand how a jet, a relativistic jet, drills a hole in the star. And many people have worked. I'm sorry that I'm not giving all the needed references here, but basically this is the picture. This is a superposition of a numerical simulation, and on top of it, I put some theoretical scheme. So the jet goes through the star. At the head, there is the shock dissipation. All the energy is dissipated at the head. It actually two shocks in term, reverse shock and forward shock. And the hot gas from this goes out, goes to the sides, so it exerts pressures on the jet and collimates it. So there is an interplay between the cocoon and the jet, and the jet does not expand conically, even so it was. So yeah, I think the connection is still on. So it's just we don't see in the room.
We can see you and we can hear you. Everything's okay. Yes.
Due to the drilling effects.
The cocoon is result from the drilling effect. It is just when you drill a hole. If I drill a hole here, then there will be a region near that will be very hot.
But it's certainly you have accretion inside. You know, from star or some core which collapsing, and you have the accretion around disk, and disk gives you the direction, perpendicular direction. This is the direction of the jet.
Yes.
I think that this will be next slide. Sorry.
No, I'm not going to the disk. The next.
Questions in order to compare to the other one.
No,
the next slide.
Because cocoon doesn't know what is the axis.
Yes.
And the information comes from the stellar rotation and from the accretion distance.
The cocoon goes along with the jet. So this is the direction of if this is the direction, the jet, and the direction of the jet is dictated by the accretion disk and what is happening in the surrounding. So this is what is setting but once there is a jet, the cocoon surrounds the jet.
Yes.
The jet, there is an interplay. The jet produces the cocoon and the cocoon squeezes the jet. Okay, so this movie does not work very well, but it's not working for some reason, so I'll skip it, but this is how this works.
Oh, we should move
there. Yeah. Now, there is another possibility of magnetic jet, and it is very important to realize that the magnetic jet are different. They also produce a cocoon, but they are typically faster and have different properties, which I will mention. Now, the jet, this is the critical issue here that I want to stress here. The jet must be, the engine that drives the jet must operate as long as the engine must operate to push the jet. If the engine stops operating, the jet dies and inside the star, and it does not get out. And this is a very critical issue. That there are two situations. Once, if the engine operated long enough to the jet to get out, one, if not. And the critical thing is the typical break time of about 15 seconds for typical parameters. I will not go to explain the values in this formula, but for typical parameters, it's 15 seconds. So you must have this black hole Newton star engine, and it must run for at least 15 seconds. Otherwise, you don't get a gamma ray burst. So this is a very critical concept to understand, that you not always have a regular GRB. Actually, as I'll argue, most of the time, the jet dies inside.
May I ask you, you certainly remember history. In the beginning, people thought there was great problem. Why, for example, if there is collapse of the neutron star or the whole, how energy is going to create supernova, especially in the case of black hole. You do not have any energy release. And then people bring this accretion disk, because accretion disk in super dense situation can produce energy, and this energy can go out and create shock. And what Tsvi is telling us that this shock initially is not spherical. It is in reality, it goes like cocoon and you know, like jet.
Exactly, and this has important implications on the structure. Now, I contrast here magnetic jet and the hydrodynamic jet. Magnetic jet, as I mentioned, propagates much faster. Typical time scale is only 1 second compared to about 10 seconds, and I will argue that observational evidence favor hydrodynamic jets. Okay.
Yes. Do you have big screen? Another display, because if you have display, you see. Or is that the second time?
Is next così in car.
Yeah, we have a
Second one is half an hour. It's half an hour, but maybe temporal, you can connect, which is easy.
Oh, I'll tell you what.
Screen,
I
then you see.
You have two screens.
I'm not sure it makes
Okay.
Let's thinking about TV, it's also because they have bigger screen. I'm not thinking about there are people very far, and I think that very good. Or you will see translation.
And what is the interaction? What is the physical process which creates the jet in the first place?
What?
What is the physical process which
I don't know.
the jet in the
Look, my approach here is to go from what we know for sure
Yes.
down. How does the jet engine operate? People have been begin to understand now how accretion disks produce jets by magnetic processes. But I don't want to go into this question.
But this jet is extremely first very porous, star is very dense, and in reality temperature is very high. It's close to BV because you create radioactive elements. Therefore, it is very unusual accretion. This is enormously high temperature. You understand? And also create waves.
So you mean that when you also
Excuse me, Tsvi, can you hear me?
It's very interesting.
Tsvi, excuse me. We are.
Oh, very good.
Tsvi, excuse me, can you hear me?
But what I want to
We have just
prove now.
Instead of a talk, we are apparently having a discussion.
This picture is correct.
But
there are several.
Jorge, can you hear me?
Observational evidence for this picture. The picture that I said, that there is a jet, that sometimes the jet gets out.
sometimes it doesn't.
And you get a GRB, sometimes it doesn't.
Doesn't, but in this case,
but in this case, you create a low luminosity GRB.
Yes.
Not only a supernova. In the cases that the jet is hidden, you.
I thought you were starting from a supernova because you
No.
have to go through the.
I don't start with a supernova. I start with a collapsing star.
Ah, okay.
I say that there is a star. The jet has to go through the star. To get a supernova, the envelope has to explode.
Okay.
I don't know yet that the
And
envelope
then
will
you have
explode.
this gamma reversed, and then if it doesn't succeed, your jet,
If
then the energy is big enough to.
If it doesn't succeed, then well, I will go into tell you later what happens if it doesn't succeed.
Screen will come and then you will see because these pictures are.
What's time of the breakout?
And not only words. I think that.
But we can see the pictures and we can even see
From here, but from there it's difficult. They are not
So the evidence, first evidence, is just in the duration of long GRBs.
Yes.
If you have a situation, this is,
Yes.
oh, okay. You can possibly connect it. So the observed time of the GRB is now difference between the time that the engine operates and the time that it takes to cross the star, which I said is about 10 seconds from this estimate of approximate estimate of the parameters. So this is the difference. This is what you observe.
So,
This means
yeah.
that from the point of view of observed duration, there will be a plateau in the observed distribution at short durations until you get to the breakout time. So this is the prediction, that when you look at duration of GRBs, the duration distribution will be flat and then it will drop. And the duration of the flat region will be dictated by this breakout time, which we can actually measure. And then we actually go to the observation. This is the duration distribution of long GRBs, of GRBs, all GRBs, long and short, in 3 different satellites, BATSI, Fermi, and Swift. And you see that in all the distribution, there is at short durations, there is a plateau. Just what is predicted, and the duration of the plateau, it's difficult to see here, but it's about 10 seconds, which agrees with the breakout time. This is just observational fact.
But there's a factor too, at least, because it's the width of the...
No, there are 3 different lines here. This is
Yes.
one detector, a second detector, and a third detector.
These 3 lines are 10 seconds.
This is 10 seconds. This is logarithmic scale.
Oh, okay.
This is a logarithmic scale. So this line go from about 1 second to 10 seconds. Then there is a correction here, and the correction here. So this is a direct confirmation of this idea. There is a correction here at short, very short duration. We see a second population of GRBs. We see the short GRBs. These are the short GRBs. They don't care about this. These are different objects. So this is why there is this increase here at short durations, and this is the slope of timing, and there is this event here, which the engine was operating. We don't see them, and these are the choked events. This is the choked events, which I'll mention in a second what they are. Now, to show you that this is not just a story, a kind of sanity check, we know that short GRBs are harder. They are harder spectrum. So what we do here is we take the whole population of the burst. You see the plateau here, and you see the short increase here, and we will cut them slowly by reducing the threshold for the hardness. So we'll take only the soft ones. The prediction is that when you take the soft ones, this peak of the short burst will disappear. This is what we expect, and you'll see it here. As I'm reducing the threshold, this is the threshold, the line of the threshold of the hardness, You see, I reduced the hardness. This did not affect it. Only these are affected. Of course, now I reduce it so much that everything disappears.
Yes,
But at the beginning, you can see that the very short one were really the short bursts, which are different population, and there is a real plateau here. So this is
short are hard and
the short are hard
soft.
and the longer soft. This was known for a long time. So this is this story, and this is one evidence for this, direct evidence for this picture of a jet going through a star. So any model that you have for a gamma ray burst, you have to explain this. So this is one feature.
So the plateau is this 10 seconds, which is required for the jet
to go through the star, because the head is subrelativistic. I didn't
understand power 11 centimeters, and we immediately find what is how much time you need. It's seconds.
So it's about 10 seconds with
giant stars. They are 3, 5, 10 times bigger than 10 seconds.
Well, some details depending on the jet structure and so on. So everything fits. I mean, when actually the whole story about this is that we came out with this model, and we were driving in the car where it was and the Sari was in the car, Rem Sari, and we told him this story, and he said, no, this is impossible. If your story is correct, there must be a plateau in the short duration population, and this plateau does not exist. We came to the university, we went directly to the data, and within half an hour, I came to his office, and I say, here is the plateau. So for us, this was really a test. We didn't come to explain the plateau. Because of historical reason, the plot of duration was plotted log instead of this, so you don't see the plateau in the original curve. You remember the original plot of Krista Kovalyuto? The original plot was this one, and if you plot on this scale, which is, you don't see the plateau.
We publish it also.
But this is but this is because you use the wrong scaling here. If you use the right scaling, you get this shape and you see the plateau.
You mean that you can see anything you want by just changing the
No,
scale?
you don't see anything you want. You ask a question. The question is the following: is there a constant number of events per logarithmic interval? This is the question to ask. If you ask this question, the answer is yes. And it does not depend on what you plot. But some plots are giving you more intuition than others. That's all. Okay, but let me try to go.
But it's interesting. In the case of short bursts, what is the plateau duration?
Oh, I did not have time to talk it. I didn't prepare it here. But for short bursts, there is also plateau.
Yes.
If you look just for short bursts, the plateau is about 0.3 seconds. I will show you, I can show you later.
You mean, and also the data?
If you, there is a different data set, you cut the long bursts, you just look at the short bursts. And if you look at the short bursts, there is a plateau of about 0.3 seconds, because they also have to propagate through a surrounding matter.
Tsvi, but I saw so
Gregor,
many.
can you intervene? This is a total chaos. I mean, they're talking by themselves. No one. You need to just stop them. You see, it's impossible.
Okay. And it is very dramatic how two neutron stars create bigger, and then Chandrasekhar instability comes and this goes out. But it is, there are all characteristic dimension is less than few times in power 6.
But
6 centimeters. How you create 0.1 seconds? Is it some envelope?
You are forcing me to jump to the last talk, to the last slide.
Okay.
But the answer to this, the answer to this is that there is enough matter which is ejected during the merger. The characteristic size is 10 to the 6, but there is some matter which is ejected.
Yes,
and this is enough. And this is enough. This is enough. This is
again gamma.
There is enough matter. There is enough matter to, and this matter is propagating fast enough to make a cloud which is about 10 to the 10 by the time the jet gets it, because it also takes time. It takes time for the jet to start going out. The jet does not start immediately. There is a delay, and this delay gives chance for the matter to expand. But this is my very last slide. So let me just give you one more piece of evidence for this whole story. And the other piece of evidence comes from low luminosity GRBs. I mentioned before 98 BW, this first event in which there was a connection with GRB. This event was the prototype of low luminosity GRB. The luminosity was about 10 to the 48 ergs, a maximum 10 to the 49. They are smooth. All the light curves go up and down, no oscillations. They are soft, much softer. The peak energy is less than 150 keV. And it is not well known. They are much more numerous than regular GRBs. Now, we see only 10 of these low luminosity GRBs, but we see them from very small volume because of the low luminosity. If you factor out that we see them from such a small volume, you realize that these events are more frequent than regular GRBs by about a factor of 10. Most of the GRBs are low luminosity ones, and we don't see them, and they are completely different animals. And the explanation for them is that we have a jet which is choked. It is producing a cocoon, and it dies inside the star. It doesn't even get out of the star. But the cocoon will break out from the star. And as the cocoon breaks out of the star, there is a shock breakout. And this shock breakout is the source of the low luminosity GRBs. Now, I have here another simulation. I hope it will work. So this, you see the jet going out, but now the jet disappeared. Yeah. The jet died out. It was shocked. And this is the moment of the shock breakout. You see the jet getting out of the short GRB, the low luminosity GRB. Let me show this now in step by step. This is the jet which we inject. It is moving. It is, now you can see clearly the shock at the front, the jet, and the cocoon. You can see the cocoon. At this moment, this is the moment that the jet disappeared. If you look here, there is no more material moving at high velocities. This is the velocity, this is the density, and there's no more matter moving at high velocities, at high, very high, Lorentz factor of 20 or more. There is no jet. But you have a cocoon which is propagating. Yes. How do you say in Japanese? Chotomate kudasai. Wait a moment, please. So this is expanding. Shock breakout. This is the moment of shock breakout. This is where we see a soft, low luminosity gamma ray burst at this moment. Now, I don't have time to go to here, but there is a beautiful work by Sari and Akar that calculate the properties of this shock breakout and compare. Here you see the observations on the left and the theory on the right, and you see this very, very nice agreement because there is some closure relationship between the total energy of the breakout, the temperature of the breakout, and the duration of the breakout. So if you know the temperature and the total energy, you can predict the duration. And this is the prediction for the duration on this ellipse here. And this is the observed durations. And you see the agreement is beautiful. And this is for a very simple analytic theory, not even numerical simulations. Right now, I'm involved with Matteo Paes, a student, a postdoc, in this simulation, more detailed simulations.
but no one shock break, even in the case of normal supernovae, wasn't observed yet.
Not yet, but let me go back to normal supernova. Rashid, you are changing the order of my talk.
It's so interesting.
Thank you.
Observe this shock break.
Thank you.
It's not observed.
It's not observed yet.
Observed in simulation.
It will, no, but a very good candidate to observe it will be ultrasat.
Yes.
Ultrasat will be in the UV and will have large enough field of view.
Yes, because temperature is of sort of 10 power 5.
Yeah.
But how do you call it a gamma reverse if it's in the UV?
No, there is a component.
Nature is similar.
There is a component in X-rays in tens of keV, and there is a very strong component in UV which will be observed. Maybe you should catch it with zero theta. I don't know.
But that UV is at what time you expect that?
What time it's going to be launched? 24.
No, I mean the UV signal. At what time do you expect that?
At the time of the shock breakout, it should be about.
Same time.
It should be, yeah. It should be simultaneous, yeah. But now to your question about becoming. As the matter gets out of the star, if the cocoon matter gets out of the star, it spreads around. It's like a blanket, and it engulfs the star as an external blanket of hot and very fast material. This is a prediction of this idea. That the cocoon matter.
It's moving this
is, yes. It's also expanding,
yes,
but also going sideways.
Yes, because the cone is open.
It's expanding and going sideways. And we saw that. We saw this. How did we see this? So we have a situation in which we have.
In simulations.
Not in simulation, in real life.
Oh, sorry, because I'm a bit confused.
We saw this in real life. In simulations, you can see everything that you want, but in real life, we see. So this is a kind of this is a simulation which shows you what to expect. You have the core here, the star, which will explode as a supernova, and it is surrounded by this hot material from the cocoon, which is also very fast. If you look at it, and you look at the supernova here, you will see absorptions line produced by this hot, fast material, and they will be very broad absorption lines. Very broad because the material is moving very fast. So you can identify the velocity of the matter and the density of the matter from this absorption line. This was seen already in 97, in supernova 97 EF, which was not involved with the gamma ray burst. This was seen in a regular supernova. And was no, it was not the famous one. It is an unfamous supernova. 97 EF. EF, which was observed in 97. Very broad absorptions line, 40,000 kilometers per second. It was published in 2000. Nobody understood it, so it was just left like this. Now, and then this line disappeared after a few days. Why did it disappear? Because the matter becomes dilute. This envelope becomes dilute. As it becomes dilute, the line disappears. So this was seen in some supernova very early on, and then this line, this very broad line disappeared. And the interpretation is that there is very fast moving material surrounding the supernova. The only explanation that I have for this is that there was a cocoon that spread this material, produced this effect. So this is the density, this is what a regular supernova should look like in terms of energy versus velocity. And this is what the contribution of the cocoon. Very fast material moving at very high velocity in addition to the regular supernova matter. And this was seen in several regular supernova, but the last thing which is, and this is a comparison of the recent calculation by Matteo Pais and some of the observations, so we can explain the energy distribution very nicely. But what is most important, that there was a low luminosity gamma ray burst associated with supernova 2017 JUK. So this was a low luminosity gamma ray burst. The same phenomena was observed there. Exactly the same phenomena, very broad absorption line corresponding all the way to, if I'm not mistaken, 100,000 kilometers per second at the beginning, and then the lines disappear because the matter spreads out. So you have disappearing broad absorption lines corresponding to matter surrounding the supernova. In my mind, this is a completely independent description of this picture, and making the link with supernova that you mentioned before much stronger, because we see this event also in supernova in which there is no gamma ray burst at all. Not always there is this soft, the question whether there is a soft gamma ray burst or there is a low luminosity gamma ray burst depends on the viewing angle and on the details of the shock breakout. If the shock breakout is not powerful, we will not see it in gamma rays, as you suggested. We'll see it only in UV, but we will have this effect or soft X-rays, and we will see this phenomenon. So this is
all the time, almost every time a star collapses, there is a jet from somewhere. Which goes out or not. And
you are jumping a little bit farther. You say all the time. I don't say that all the time, but I say in many supernovas there is a jet in addition to the whatever going on at the center of the supernova. Now, let me take you to the future, how we see the jet. We will never see the jet directly, apart from one way, gravitational waves. Because the acceleration itself of a jet from rest to speed of light produces a unique gravitational wave signal, which
induced by the.
There is a jet. You produce the jet. I don't know how, but once you make matter move from 0 to speed of light on a short time scale, this produces gravitational waves.
Due to the acceleration.
Due to the fact that the matter moved. I mean, Tim U is not constant. It's not even. It's not exactly quadruple moment because it's a speed of light. So you have to go beyond the quadruple formula. But this gives a unique signal which I call jet GW, and so this will produce gravitational waves. And if we are sensitive enough, we can measure them. They will be kind of jump.
But they will not be collimated themselves?
No, the gravitational wave will be anti-collimated with the jet because of the quadrupole nature of the gravitational wave. So there'll be
not only quadrupole, but it's
yeah, but it's not only quadrupole. But roughly speaking, they will be anti-collimated with the jet. We will see them best if you look from the side, not from this. And the problem is that they are usually at low frequency below LIGO. Below Earth detectors. They are, because of this jet that we are talking here about, they are the frequencies of sub-hertz. You cannot detect them on hertz, on the Earth, but you have to go into the future. The future will be DECIGO, which will be space detector in 0.1 hertz, or something even more crazy, which I'm small part of, lunar gravitational wave detector. The moon is very quiet, so you can measure in these frequencies. So there will be, we have some, it is led by the head of Virgo, Castanevas, yeah. So there are 3 proposals. One of them is led by Castanevas, the head of Virgo. And what we are proposing, some futuristic gravitational wave detector on the moon, which may detect this.
And this is also the opposite side.
No, you don't need
it. Doesn't matter.
Doesn't matter.
There is thought that you will get some influence from the Earth.
It's not It is a very prototype idea yet, but it's an idea which is definitely worth exploring. So, now,
Professor, you have the speakers of your computer are on. I mean, I know if because I don't know if they tell us something.
No, I'm just finishing.
They can, yeah. Okay.
Okay. Now so this will be the future, and if this works, we will be able to see a supernova at a nearby galaxy at 10 megaparsec, and we could such a detector could be sensitive enough to detect gravitational wave from the jet of a supernova in a nearby galaxy, so we will know that there was a jet inside the star. All the story that I'm telling you, that there is a lot of evidence for it, we will actually we can see it directly if we build these detectors. The last thing is now to Rashid to answer you.
The first signal in gravitational waves would be the collapse of the star itself.
Yes, the collapse.
How does it relate to this frequency and strength?
The collapse will be at higher frequency. The supernova signal will be at higher frequency, so it should be at the LIGO Virgo kind of range. So from this point of view, it will be easier to detect but depending on your supernova model, and there are very big differences. Some supernova model give very weak, because of symmetry, give very weak signal from the collapse itself. So it is possible that this signal will be stronger in amplitude than the supernova signal itself. This does not tell you about the easiness or difficulty in detecting it because of the different frequency ranges. But it may be more stronger in a larger amplitude and even larger energy. Because this depends on supernova model. Of course, if the supernova is extremely violent and non-symmetric, then so this is this story, but it will be very good because the combination could tell you, it will be like a tomography of exactly what happened in the supernova.
Different instruments, so working in different regimes.
Yeah. So the last statement, the last remarks will be an answer to you. I told you that you wanted to hear about my last slide, gamma ray burst 1708, 17A.
For which are several different models.
This was the one that accompanied the possible detection of gravitational waves, right? This event, as you can see here, was much less energetic and much softer than all other short GRBs. It reminds you something? Low luminosity GRBs are much weaker and much softer than all other long GRBs. Mm-hmm. So there is exactly this relationship. And what this line shows here, that if you try to associate this to Doppler boost, just to say I was looking at it from the side, so there is a different Doppler factor, you cannot get by Doppler boost to the regime of regular GRB, of regular short GRB. It will be, if you boost it enough to get to the energy range of the photons, then it will be much too energetic in terms of the total energy. So you cannot combine the two things. So it is not just Doppler boost. It must be a different animal. And my interpretation, and I don't know any other good explanation to what is going on here, is that we didn't see the jet directly. We were looking at it from the side. We didn't see the regular gamma ray burst. We saw a shock breakout of a cocoon that was formed in this matter, which was ejected in the merger. And this breakout, we can calculate what's happening when the material was at a distance of about 10 to the 10 centimeters, 10 to the 9, 10 to the 10 centimeters from the central core. And this requires that the jet here was delayed. It did not just go immediately. It was slightly later after the event. So this is the end of my talk, and this is the summary, and which I linked regular long GRBs, collapsars with low luminosity GRBs. The related phenomena, but in one case the jet goes out, in the other case it doesn't get out. I related this to supernova, and I mentioned that there was regular short GRBs and low luminosity short GRBs, and it so happened that the very famous one, 170817, belonged to the unique population of shocked event. Thank you. Thank you.
Okay, thank you, Professor Piran. I think every possible question was asked during the talk. Therefore, we must.
Okay, Gregory.
Yes. Can you hear me? Okay.
Yes.
Okay, thank you, Professor Piran. I think every possible question was asked during the talk. Therefore, we must move to the next talk. And this is Jorge Rueda. Yes, you have now. Well, Jorge, you can see the coffee break is planned at 10:50. Therefore, you can speak maybe for 15-20 minutes if it's okay with you.
Is it okay with you to speak?
Okay, I mean to
Yes, because we are a little late now with the program.
Gregory, can I have your questions?
Shen, maybe at the coffee break, let's Jorge speak now.
What time is coffee break?
In 15 minutes from now. Quarter hour, yes.
I think that your talk was at least 3 times longer than.
Not 3 times.
It's 5-4 because I started discussing.
If
maybe Jorge can speak 15 minutes now and the rest after the coffee break. Yes?
We have all of the people. Okay. No, it's okay. I can.
Okay, so let's have Jorge Rueda now for.
Gregory.
Yes.
So I will
because at the end of the day you are going to detect gravitational relations.
Yes, Jorge, we can hear you.
Well, I can try and then we see. Well, you should stop sharing your screen, otherwise I can share mine.
Yes, please. Share your screen.
So I will try, okay? Otherwise you stop me, we can break and then I finish. But I will try to short.
Okay.
To short it anyway, okay?
Let's do. Yes, please switch on your camera and if you can share the screen, please.
You see my screen now?
Yes.
Okay.
But we cannot see your webcam.
No internet, but so your webcam.
Can you please activate your webcam? Okay, great.
Okay, I don't know if you see me here.
Yes, we can see you. Yeah.
Okay, so thank you. So I will prepare a lot of slides, but okay, let's see. I will jump some of them. I decided to celebrate this Professor Ruffini birthday to tell you a little bit what we have been doing together during this year. So I arrived in 2006 for my PhD, and since then we have been working together in different fields in relativistic astrophysics, mainly on on phenomena related to neutron stars and compact objects in general. So we have published something like 100 papers together. So we have been really working a lot during this year.
More than me in the lifetime.
More than about in this direction. So I'll tell you a little bit. I cannot go into any detail, all details of all these things, but just tell you more or less what have been or roadmap during this year. Okay? This will be a pleasure for me, really. Professor Ruffini has been a continuous guide and support for me during my early career. So I'm really, it's a pleasure to tell you a little bit about this. So it's not going ahead. Okay. So okay. So we start when I arrived to Italy. Okay, they were discussing. You see this picture. Gregory is here. Gregory Sheshen. This is Vladimir Popov, and here is Remo. Discussing about we were discussing about super heavy nuclei at the time. How ability of super heavy nuclei, and because with super heavy nuclei they develop strong fields, strong electron.
More than 177.
No, it is super heavy nuclei of the order of mass number 200, 300, something like that. And they were developing this possibility of extending the treatment of super heavy nuclei to macroscopic system. So 10 to the 57. So this was the issue actually. So how to go from a model who was nuclei, heavy nuclei, super heavy nuclei, and how to develop this, generalize that to go to macroscopic system with stars, compact stars, because we know compact stars will have all the interplay of fundamental interaction. So from the model of nuclei, super heavy nuclei, we have the clue how to treat strong interactions. Okay, so we were trying to extend that, and in particular to see what happened to this electric field. We were looking at this because we have been always look at compact stars, the neutron stars, as objects without any electromagnetic field, electric field in particular, because magnetic field have been considered always, but not the electric field. But what happened to the electric field? You have charged particles inside, so why it should be a zero electric field or negligible electric field? So we were thinking about that, how to deal with that. So we start from the nuclei, and the idea was to extend, start from the classic Thomas Fermi model, of the atom. So because you have electron, you have the nuclei, and that was a model how to treat that from the statistics point of view. So a statistical model. So we start to study this this Thomas Fermi, which is really simple. So consider a gas of electron, which is degenerate, and there is the equilibrium condition for the electrons of the Fermi energy of electron has to be constant in size, and from that you get the solution from the Thomas Fermi model, which works very well for nuclei. So and then we consider extensions. So one of the extensions that we considered was the special relativistic. So adding this, going from non-relativistic case of electron to a special relativity. So and then in doing that, we were generalizing like a new equation of the state for white dwarf, for example. For white interiors, you consider the nuclei. And then the electrons around, but in this including special relativity, and solving the equations from the Coulomb energy and all this. To establish a condition for global neutrality of each of these cells inside the star, and at the end you can compute the pressure and density at the walls of these imaginary cells, Wigner size cells, and you can compute that. This was actually again an extension of the Feynman metropolis stellar work of 1949, and so there was an extension to that, and also an extension of the Salpeter equation of the state for white dwarfs. So, but we want to go to the stars. So we were thinking, let's make this gravitational Thomas Fermi model. So was an analogy in the sense that you establish a condition of equilibrium. From the condition of equilibrium of the fluid, you construct your field equation. That actually, this is you see here, this was similar Fermi energy, but instead of having the Coulomb potential, you have now the gravitational potential in equilibrium for the equilibrium condition. Then you have the same, and you get it's just from the Poisson equation, you get just a generalized Thomas Fermi or a Thomas Fermi model, but gravitational. So and actually you can solve using the same techniques as in Thomas Fermi model, but for stars. So at the end, what you have are the same stuff as in the you get actually similar the same by choosing making a change of variables. You can end, for example, with the Lane-Enden equation that we know is you can reduce the equation of equilibrium of a self-gravitating body to Lane-Enden equation. So and this was good. I mean, we can really do that. So and then we extend again. Let's go to special relativity. We make the special relativistic gravitational Thomas Fermi to include special relativity to the Thomas into the statistics. So to be able to go bit by bit to realistic general relativistic stars. So from this, just from this generalization, of course, we can recover the critical mass, the concept of critical mass already there, and actually.
But this is still there?
No, not now, not yet. So yes, we will make the analogy and change the Coulomb potential by gravitational potential at this stage. Then we will include both. Okay. So we make the complete analogy first. Let's change the Coulomb potential by gravitational potential.
But the difference is that heavy nuclei is the difference between star and moon.
There are two things. First, you take a microphysics, and we make extension. We make we put a special relativity and make a new equation of the state for you have ionized matter, let's say. And that was one goal.
So you started with heavy nuclei. So
yes, any nuclear.
Oh.
Any. It doesn't. You don't need it to be heavy, but of course it works better if it is heavy because it is the approach of statistical approach works better, of course, if it is if they are heavy nuclei.
Okay, so then you jump to something which is not heavy, but special relativity.
Now,
and then you jump to anti-gravity.
Now, just we change. That was something a model for the interior matter.
Yes.
We want now to make a model of the whole stuff.
Yes.
Okay, and then so we say, let's assume that these are fermions. Okay, this big thing is made up of fermions. So and let's think only about the gravitational interaction between them. So we make an analogous model in which the equilibrium condition is given by the gravitational potential. And this is the equation here. You can see that you see here. You have the kinetic energy plus gravity, the potential energy must be constant through the configuration. And from that, you get the equation of equilibrium of the system. Okay, but here we have only gravitational energy, gravitational interaction only here between the particles. Okay, then you take the relativistic limit and you end with the concept of critical mass as usual. Okay, so you can recover from this kind of picture all the what we know. Actually, you recover the entry Lane-Enden polytrope from this gravitational Thomas Fermi model. But we want actually to go to the general relativistic case. This was our goal was to go there, and we did that. we want to make us construct, let's say, an analogous model to this, to the Tolman-Oppenheimer bond, because you see here, because from the special relativity plus Newtonian gravity, you end with the wrong critical mass. For example, for the case of neutrons, we know that you go through critical mass is 5.8 solar masses. For that case, we know the critical mass of neutron stars is much more than that because of general relativistic effects. So we want to do that, but so we challenge was to change that, and now we try also to include also the electromagnetic interactions. So not only gravitational. So we just was to include in the equilibrium condition that this Fermi energy, constancy of the Fermi energy, include also Coulomb potential. So because in the neutron star, for example, in the neutron star you have neutrons, you have protons, you have electrons, you have different charged particles. So you have to include to put these equations of into the equations of equilibrium for each particle, for each species that you have in the system, and guarantee that this generalized Fermi energy that is nothing else than electrochemical potential, including gravity, must be constant through the configuration. And you have to solve this condition, this equilibrium condition together with the field equations. We did that for white dwarfs. So I now have to go fast. So this is a mass central density mass value relation for white dwarfs. So we included also beta equilibrium condition. We include different, completely the physics of white dwarf, for example. And then we move to neutron stars. So we first solve neutron, protons, and electron gas in beta equilibrium and include Coulomb potential. We look at the electric field that developed inside the star. This sedimentation, you have sedimentation of protons and electrons inside the star gives a balance. That must be balanced by the presence of electric field inside. So you see the Coulomb potential, macroscopic Coulomb potential inside the star, and actually you can write it in with a beautiful formula. And from the beautiful, yes, this is global neutrality instead of local. Yes, this is you have to do that. Then we move to include also, that was without a strong interaction, that we would include a strong interaction. So we did it with some relativistic, you need some relativistic model in such a way that you can incorporate it correctly with in a general relativistic picture. So you have to choose some, nuclear models, you have so many, you have some relativistic and relativistic. So we have to pick up the relativistic one. So this is an example of that from relativistic field theory. And well, you can do that and generalize, you keep generalizing. You see here the potential now, let's say Thomas the constancy of Fermi energies of electrochemical potentials. Actually, we call them Klein potential because of the word of Klein in 1949. We showed that the chemical potential must be constant in a general relativistic system. So these are generalized Klein potentials or Fermi energies, as you like. And here you have this generalized, this is only put the energies, the potential energy that includes gravity, Coulomb potential, and a strong force potential. Well, but in the neutron star, you have the core. This is what happens in the core of the star, but then you have the crust of the star, and they have different physics. So you have to match these different physics. And actually, I'm not sure this is if this is the unique solution for this problem actually, but this is a possible solution. That there is a transition between the core and the crust of the star. There is a very tiny region in which the electric field has to peaks to a very strong value and then dies. Okay. This is one of the solutions because you have to match the Coulomb potential from the core going to the Coulomb potential of the crust, and they are different. And then you have to match them. The one possibility is that you have this drastic drop between the two, in very tiny region of a few femtometers. So you have that. I'm not sure these are numerical solutions. I'm not sure this is the only possibility. Maybe you can match also with mixed phases, maybe. But we don't know. But this is certainly a nice possibility when you have this field that can be largely overcritical between the two. And this has consequences on the mass radius relation of the star because you have.
What happens to trade pairs in this transition level?
No, not at this point because you have everything is all this you have the occupy completely the phase space here because everything is degenerate. So you don't create pairs at this. Of course, if these fields, if by any chance these fields gets open to vacuum, of course it will create pairs, but not inside here. But
you have macroscopic electric field.
Yes, you have inside macroscopic inside the core, but if that field is low, it's something like 100 volts per meter, 100 volts per centimeter, sorry, 100 volts per centimeter. But then in a very tiny region, it can spike to overcritical, but a very tiny region, just to match, to guarantee that you have the match of the electrochemical potential constant throughout. This is
what is the reason for the charge separation that is causing the macroscopic electric field?
That is segregation that you have between the charges, between the negative charges and the positive charges, and you have this balancing field. It's just from the solution of a gravitational equilibrium. If you put gravity and you put Coulomb field, this develops. This was called gravitopolarization in the 1920s, actually. So 1920s. Classically.
So this changes the equation of states, I guess.
Well, it has no real effect in the equation of the state, actually, because the electric field is low.
So the critical mass is the same as usual.
It changes. Yes, exactly. It changes the radius.
Okay.
It changes the radius.
Because at the end you must find something observable.
Yes, you change it. You can change the radius. You can see here the two cases, for example. So it depends on about how boundary conditions you have different kinds of solutions here. So
Jorge, excuse me. You have now already in the time of the coffee break. So let us know.
Well, if you like to stop.
As you prefer. Actually, coffee break may be useful for you, people local, but we can follow anyway the talks. So just let us know how you prefer to.
So let's.
What time is the next talk is scheduled?
11:05.
Because we cannot make the other person wait.
No, I am the other person. I can wait. No.
So you conclude in 2 minutes.
I can try to make let's quantum jump.
Okay.
A quantum jump now. Well, just to mention. This we made a series of represented here in the Korean meetings in the 12th and 13th Italian Korean symposium. Here we continue to work on this, but not only on the physics, but on the astrophysical consequences of some of these things. So we keep working. We did some more other works on white dwarfs, actually investigating also the stability and the presence of strong magnetic fields inside the stars. We make also some a wider model for the explanation of magnetars, actually, and we made some works on that. Our explanation was also white dwarfs could be explanation of soft gamma repeaters and anomalous X-ray pulsars, but also normally rotational power pulsars could explain them. Some of them, something like a half of the population.
This
is white dwarfs, and we were making a series of works on white dwarfs and neutron stars, but this is white dwarfs now. So you see here, this is about finite temperature effects in low mass white dwarfs. These are 0.9, 0.18, 0.2 solar masses white dwarfs. You can see the temperature effects in the mass radius relation, and you can measure that. This was a nice case of that. Rotation also, so we made some work.
So does this make a difference? Because if I guess I'm not an astrophysicist, but everybody has understood. If the temperature that you predict is not the same as the standard one and there is no global electric field, this can be probably seen because of one sees the temperature of the star.
Well, in this case, for example, when you have the low mass white dwarfs, in this case, these finite temperature effects dominate. When you look, see, because the effects on the rays is really huge in that case. So that effects is overwhelming over any other.
So what does it affect? Because my question again is, what is the difference between a standard white dwarf model and yours when you add the global electric field inside the star?
No, in the case of white dwarfs, it's small. In the case of you have an effect on the equation of a state. Okay, for example, in the case of white dwarf, when you consider the interior electric field, it changes a little bit. Like 1% the critical mass.
And the radius?
Like 1%. The radius doesn't change very much.
Okay, so it doesn't change anything.
That doesn't change almost not.
And what about the magnetic field? Because I guess
it's important to consider correctly for the equation of state effects, because when you go to low pressure, for example, if you go to low density, the low density part, if you take a Salpeter equation of a state, for example, that is a successive approximation, you end with negative pressure to unrealistic values of the pressure. When you do this thing correctly, how to introduce that, you don't get that. So to treat low density and low pressure in white dwarfs, you need to treat this in proper way. The Coulomb correction. So you have to do it numerically. Not with the Salpeter equation of state, you cannot do that. So to go to this regime, you need to do this correctly. But the finite temperature effects are overwhelming. They are dominant in these stars. Then you have rotation, magnetic field. You have these are model of magnetars with white dwarfs. Then you have merger. We were also to mergers with white dwarfs and make some electromagnetic analysis of the signal that you get from white dwarf mergers. We are still working on that. What you get in the optical, what you get in the X-rays, what you get in gamma rays, and also the different possibilities that you have to merger. You can get a super Chandrasekhar object, a sub Chandrasekhar, or you can go into a neutron star, and we look also to the possibility under which conditions you make from white dwarf binary mergers, you get a supernova 1A, or you don't get a supernova 1A, but a different kind of post-merger evolution. So this is what you will see here. So we are also have been working on that. Well, these are neutron stars now. We did also more neutron stars on.
Can I ask a specific question? Because from what I understood, G talked about the famous gamma ray burst, 17 or 17. And from what I understood from Remo, that you have a model of two white dwarfs.
Yes.
And this is the model you have for this gamma ray burst. Am I correct?
Yeah, that GRB 17A, 17A, only the GRB part. Okay, only the GRB emission. Yes, we made a model based on white dwarf with a white dwarf merger. Yes, because you have what you have there is something similar to this thing, to this picture actually here. If I can move this.
I'm sorry to insist a bit on that because
yes, you have when you have a white dwarf merger, then you have this. Professor Piran was mentioning that you have this material that is ejected. He was mentioning that for neutron star mergers, but for white dwarfs it's the same, or for neutron star white dwarf merger it's the same. You have some material that is ejected. In a white dwarf merger, you have something like 10 to minus 3 solar masses that are ejected in a white dwarf merger. And this material it cools down, so it cools down and has some optical signal. If you have the object that is formed at the center, so they will also inject energy into this and heat up this matter, and that's what you get an optical signal from that.
And when you look at this white dwarf mergers, do you have your global electric field, or just standard?
No. That's the standard. That's the standard, because you look just at the matter that expand. I mean, just a normal density, pressure evolution, normally completely, I mean, standard. What is important is that you have a heating source at the center. So you have some, because we expect that you form some massive rotating white dwarf at the center, for example, with some magnetic field. And so it acts like a pulsar. It injects energy into this matter. It heats up this expanding material. It cools down. And this cooling, it shows with a very similar signature to the one of this kilonova. It's not a kilonova from the sense, in the sense of our process, nuclear decays, but it's in the sense of the picture from the point of view of the colors, from the point of view of color evolution, and from the point of view of the luminosity that you get from that. You get something like 10 to the 42 wave per second, peaking at half a day, actually half a day, something here. So something very similar to what was observed in that GRB. And actually, these white dwarf mergers, I consider, this is my personal opinion, they are something like underestimated objects in astrophysics, but actually very, very interesting. Because and now is especially interesting, because now we have these facilities in the optical that can reveal these fast optical transits. And white dwarf mergers, we expect them to be very numerous. So this is something that we expect, like something like 10 to the 4, 10 to the 4 and 10 to the 5 objects per gigapixel cube per year. So they are extremely numerous. And so with these new facilities that for fast optical transit, now that I think that we will start to think more about white dwarf mergers. So we are working in this direction to know more and more and more about the white dwarf mergers, not only from the optical, but also the connection with the X-rays, and to see how we can actually work together between the different bands and with the different instruments to see if we can pinpoint actually these white dwarf binary mergers.
Jorge, excuse me. Now we have, according to the program, Narek's talk. So maybe we can you can finish in few minutes your talk. Okay.
Well, I just let me just
just to follow the program.
I will introduce the final part, because I will want to speak on Wednesday.
Yes, we can.
Yeah, so I will.
I can give you some minutes from my time.
No, don't worry. I will stop here and I continue Wednesday. Okay. Because Professor Piran was speaking about gamma ray bars. So some point, and then start to look at the astrophysics binaries, also in mergers, all these things. And in the last years, we have been working very much on a model of gamma ray bars based on a binary system, which includes the physics of neutron stars and black holes. So this will be, I will speak about this on Wednesday. I was planning to mention this today, but there is no time for that. So I will shift that to Wednesday. So, but just to mention that we will be using this what we have learned about neutron stars, black holes, okay. So we can.
Thank you, Jorge. Are there any questions in the meantime from the audience? Maybe one quick question from people connected on the internet, because there are questions asked by people locally, answered immediately. So maybe on the internet, if you have some.
Manuel.
Yeah, I did that. Yeah,
Yes, Manuel,
Jorge,
please.
Hi, Manuel. I just read your question. Your question was the same as here Professor Nathalie that was looking for some signature of this superelectric field, supercritical field. Well, not directly, but there is the effect on the radius of the star, or maybe there is so there can be some signal in the maybe in the collapse. In the gravitational collapse, or we don't know yet, but you need to leave that field. The electric field must to be open, let's see, not to be more any longer into this configuration with the degenerate matter, because in degenerate matter it can do nothing. So maybe if in the collapse the matter gets let's say free, then this for some maybe for some transient it could make some transient.
But could you have some electron positron emission?
Yes, it might be, but not in the normal star, but maybe in the collapse, maybe. We never studied that, but there is that possibility.
Okay, thank you.
Yep.
Okay, thank you, Jorge. Let's move to Narek.
So we have 15 minutes?
You mean coffee break?
Yes.
Actually, we use the time of the coffee break already. So if you prefer, you can do that, but then we should ask all the speakers to speak shorter.
I will make my presentation shorter. Grigori,
okay,
don't worry.
okay. 10 minutes then is okay. Okay, so we meet at 11:20. Is okay with everyone?
Okay.
Okay. Let's have a break. Hi everyone. Can we have the people in Nice online? Hello. We should keep the schedule. Next speaker according to the program is Narek Sahakyan. Narek, can you hear us? Hello.
Hi, Gregory. Let me call him. Okay.
Yes, Jorge, please.
Android AP, password is JARH. R. In lowercase.
Hi, Gregory. Can you hear me? Or can you mute your?
Yes, we can hear you, but we have echo from other computer.
Yes, not from your computer. From your computer. Just mute your computer. No. I'm still in front of the camera. It's true. The connection. Okay, Gregory, now it's fine?
Yes, now it's perfect. We can hear you.
Just wait 2 or 3 minutes. The people are outside taking a coffee. They come back and then we can start, okay?
Well, we are already beyond the schedule, so please try to
yes,
be on time.
Just a second.
In the meantime, why don't you share the screen and show?
I'm trying to do so.
Okay, we can see it.
So Gregory, you see my screen?
Yes, we can see your screen. You can start as soon as ready, okay?
You see my screen?
Yes.
Okay, I think we are using the internet and we have a very unstable.
Here we can see full screen, yes. Narek, we lost you, Narek. Excuse me, Narek, can you hear me? Jorge, can you hear us? Apparently we lost the connection with this. I think we are having problem with your connection with Nice, so we should move to the next speaker, who is Rahim Moradi, and I think he is going to join the meeting. Let's see.
Gregory.
Yes, Narek, you're back.
Gregory.
Narek, you're back.
No, Gregory, we have internet problem. So the phone.
Yeah, we noticed this.
It does not work anymore.
So you have no connection, right?
No, it's impossible. We continue.
Okay, we will probably wait until your connection is back. In the meantime, we keep going with the meeting, and we try to have Rahim Moradi now as a speaker. Rahim is in Iran, and he's also having some connection issues. We're checking with him. We have also Pixin Chen from Taiwan scheduled to talk after him. So if Pixin is online, please be ready. And we're checking with Rahim if he can connect. Rahim, can you? No, I think we don't have neither of them. Maybe we can, in the meantime, we have another speaker. Ye-Fei, no, we have in the program, just let's see who can speak now. None of the speaker apparently is ready. Pixin. Now Rahim has sent me a presentation. We cannot just sit and wait probably for a new speaker. So let's see if we have other speakers available later in the program. We will have, if Professor Chen is not available, in the lunch time, we have several speakers, who is Professor Zakharov, Professor Rafelsky, Grant Matthews, Massim Belavalle, Stefan Ansoldi. Maybe we can have Alexander Zakharov now for 20 minutes.
Okay, it's now.
Do you mind? Okay. So let's start with Alexander Zakharov, and then we'll see if other people will be ready
So
to
I
connect.
will try to share my screen.
Please.
Okay, just wait. No, sorry. Sorry.
No, it's okay. We can see your screen.
You see my screen?
Yes, we can see.
Okay, fine. Full
Can
screen.
you start the full screen, the slide? Yes.
Okay, I'm trying. It's waiting. Wait. It was unexpected time for me, but it's okay. I'm still waiting. Okay, it's okay. It's full screen or not?
Not yet.
Now?
Yes, now we can see it. Yes.
Okay, I will try. Okay.
Okay.
Thank you very much.
You have 20 minutes, please.
Okay, good. First of all, I would like to thank organizers. Do you hear me well, Grigori?
Yes, we can hear well. Yes.
Okay. It's first of all, I would like to thank organizers for nice opportunity to be here and to present this talk. So it's connected with the recent result of Event Horizon Telescope. You see, recently, a few days ago, they showed a shadow for the black hole, the galactic center. So, but this conference was devoted to 80 years since Professor Ruffini birthday, and he had a huge influence on Soviet astrophysics, because in 45 years ago, his book with Martin Rees and John Wheeler was published. It was really, it's a book, Russian translation of this book. But here I would like to emphasize that in Soviet times, it was very strong, strict selection of books of foreign authors for translation. Only famous scientists, books of famous scientists were translated into Russian. But also, you see, in 1979, Italian publishing house collected contribution of famous authors due to 100 years since Einstein's birthday. And among these authors was Professor Remo Ruffini. And also this book, exactly 40 years ago, was translated from Italian. And you see, if you take a look at envelope of this book, you could recognize famous picture of Professor Ruffini, which was practically a logo of ICRA and Marcel Grossman meeting as well. So it's Professor Ruffini paper, it's a Russian translation. It's also, it was almost exclusive case because basically English book were translated into Russian, but not Italian ones. But also probably, especially for Grigory, it may be interesting that editor of this book was Belarusian academician Fedorov. But here you see also these pictures of trajectories of particles near rotating a black hole. You see, and you could recognize that gravitational field near black holes are very complicated due to these trajectories of lights. But how to recognize, how to evaluate gravitational field in astronomy? It's also, you see here, you see this picture, which is logo of ICRA and also Marcel Grossman meetings. But you see, and also it's also confirmation of these claims. But how to recognize gravitational field? How to evaluate it? In astronomy, we could only observe, sometimes with very advanced facilities, but sometimes not. But by the way, we cannot organize this experiment as in physics. For instance, in physics, we could launch particles if you have black hole in our hands or in laboratory, and we could launch particles and they have to move along these trajectories. That is, but also you see, in 1988, Soviet Academy of Sciences organized conference due to celebration of Alexander Friedman. It was organized in in Leningrad, and here you see Professor Remo Ruffini, Alexander Dmitrievich Sakharov, and Igor Novikov. But also there were very intensive conversations between Soviet scientists and foreign ones. And here you see Alexei Alexandrovich Markov. He was an academician secretary of nuclear division of Soviet Academy of Sciences, and Professor Remo Ruffini at this conference. Very intensive conversations. But Markov was editor of, let us say, proceedings of this conference. But what about gravity law? You see, Kepler established gravity laws, and Hooke said that maybe described with this force, with this law. Now we call it like Newtonian law. And Hooke tried to prove that is, according to this gravity law, probe particle has to move along elliptical curve. And also Rutherford did this experiment. He considered beam of alpha particles, and after that he evaluated interaction between charged electrons and positive charged nuclei. How to probe black holes? There are three basic techniques to trace stars around the black hole, to take a picture, which was practically Keck collaboration and gravity collaboration did this exercise, and leaders of these groups got Nobel Prize for these studies 2 years ago. But recently, you know, a few days ago, Event Horizon Telescope people evaluated shadow size for galactic center, but 2 years ago they did it the same things for M87 star. What about results of these people? Also interesting thing that observations of these groups were done in April in 2017. That is two images. That is Sagittarius A, it's a new result, and M87 star. What about their processing? So analyzing VLBI data, they did 4 different images for this source, and averaging all these results, they did it, and that is average picture for these results. But what about shadow? Well, probably one of the first person who considered this case was Jean Luminet. So that is important thing, that is separation of scatter and captured photon orbits. There is a critical impact parameter which separate scatter and capture. So, and also one of the first person who considered formation of shadow were Falke Melia-Gol. More than 20 years ago, they considered formation of shadow in numerical way, that is for millimeter band and for centimeter band, and you could recognize that there is no chance to detect shadow for centimeter band. Why it's important? Because it was a Russian project, radioastron, but the shortest wavelength was around 1 centimeter. In this case, as according to Falke Melia-Gol simulation, there is very little chance to detect shadow. And our proposal in this year, we proposed to detect shadow near the galactic center, because shortest is too short, but probably it may be detected with millimeter wavelength interferometry. So that is our paper. What about type of shadow? That is classification of different Chandrasekhar parameter which separates scattering and capture. And and here you see, assume that our distant observer is located in equatorial plane. In this case, its solid line corresponds to extreme rotating black hole, but dotted line corresponds to Schwarzschild case. It's well known from textbooks. But if our position of distant observer is very near to axis, polar axis, in this case, you have very weak dependence, size of shadow as a function of spin, as it was done in recent observation of Sagittarius A, as we know now. And if there is an intermediate spin parameters, there is very weak dependence, size and shape of shadow as a function of spin. But if spin is high, there is a visible dependence of size of shadow as the function of position angle. But here you see, we in this paper, we also predicted that this kind of type of shadow may be detected in millimeter and sub-millimeter band. Of course, we cannot detect darkness, but we have to detect phases, or we called it like mirages around this darkness. So, and then also is an interesting thing that if there are charged black holes, Reisner-Nordström metric, there is analytical expression, size of shadow is a function of charge. And so that is, F charge is high, so size of shadow started to be smaller. And but also I'm repeating that there is analytical expression for this case. But later on, people suggested so-called black holes with a tidal charge. In this case, Q squared may be negative. And also so-called Hardetsky theory, where there is a scalar tensor theory, it may be considered the same parameter Q, which may be negative. And also that is illustration that its dependence as a size of shadow is a function of charge. Very often people proposed wrong pictures of black holes because its farthest part of accretion disk always should be visible, but it's people use it anyway, and even Event Horizon Telescope people are using it sometimes. But you see, that is correct image of black hole accretion disk, which was reproduced by Kip Thorne and his co-authors. And here you see shadow, because this accretion disk is cut. It's not until the last stable orbit. But Event Horizon Telescope observations, they done these observations, VLBI observations, and after that they emphasize there is infinite number of possibilities, but they selected the most probable, the most likely interpretation of the observational data. About 2 years ago, they reconstruct image for M87 center, and they proved that mass of black hole, in this case, 6.5 10 to the 9 solar masses. So that is VLBI network, which was used in these observations and also in observations of Sagittarius A star. And also I'm repeating that there is dependence, size of shadow is a function of charge. But also 1 year ago, Event Telescope people evaluated charges or parameters of metric in spherical symmetrical cases. They show, here you see blue curve corresponds to Reissner-Nernst metric, and also some alternative. So, but also important thing, they showed limits on parameters. Limits on parameters using constraint on size of shadow. So that is illustration of this result. If we consider different metrics for black holes, and if we consider, for instance, our shadow is an allowed interval for Event Horizon Telescope, that is suitable model. But if our shadow is smaller than allowed, in theory, is smaller than allowed region for Event Horizon Telescope shadow, it has to be rejected. Also, these results were generalized for tidal charge, used our analytical expression for size of shadow, and also we could say that is in this case, that is a restricted area for tidal charge. Only this interval, that is light green region. And but in observations, we used this estimate of size of shadow. So, and also recent report of Event Horizon Telescope people, they did it for Sagittarius A, and they said predicted size of shadow predicted based on estimate of mass and distance done by Keck and gravity people, and that is constrained on shadow size from the observations. So summarizing, so I said almost everything. We could say that a few months ago I said that the Event Horizon Telescope will release this image, but it was done for Sagittarius A. And at the end of my talk, I would like to wish happy birthday, Professor Remo Ruffini, good health, and I wish him fruitful years and new breakthrough discovery. Thank you, discoveries. Thank you very much for your attention. Thank you.
Thank you, Professor Zakharov, for the interesting talk. We have time for a few questions. If anybody has a question, you can just directly ask them. or write them in the chat, please. We apparently have no questions. Well, thank you anyway. It was really a nice presentation. And yes, we are aware, by the way, the book you mentioned in Russian, this was indeed translation made in Belarus at that time, part of the Soviet Union. And I know the person who made this translation. It was really very nice.
Okay,
This
okay, thank you
recollection.
very much. Thank you.
Thank you. Okay, now we have next speaker who is Rahim Moradi. Rahim, can you please activate the camera and share your screen?
Hello.
Yes, we can see you.
Hello.
Very good.
Unfortunately, there was some problem with my connection, so
yes, but now everything's
make it
solved.
on time.
Very
Sorry
good.
for that.
Please show the screen.
And, let me. I'm not sure if you can see. Can you see my screen?
No, not yet.
I have already shared. Let me share it again.
Let's try again. Yes.
Let me turn off my camera, maybe you can see.
Let's try.
I don't know what's going on.
Well, you actually sent me the presentation. I can show it if you like, and then.
Yes, I think I can say next if you can.
Yes, yes, and switch on your camera in the meantime, and then I will show. I will show the screen. Can you see it?
Yes, that's it.
Also, now you can see, right?
Yes.
Full screen. Okay.
Okay.
You
Hello,
may start.
everybody. Yes, hello, everybody. Thank you for giving this opportunity to me. In the purpose of Professor Ruffini's 18th birthday, first of all, I say happy birthday to Professor Ruffini, which I have learned lots of things from him, which during my presentation, I will mention some of these precious things that he has taught me. Can you go to the next one, please? Okay, this is a work about GRB 180720b as an example to show more details about binary driven hypernova type 1, a model that is developed mainly by Professor Ruffini, Professor Rueda, and the group that I have listed here, and also many other people. But specifically for this GRB, my collaborators are Liang Li, myself, Jorge Rueda, Ruffini, Narek Sahakyan, and Wang Yu. Next slide, please. Okay, this GRB 180720b, why we call it binary driven hypernova type 1, before going on to the details. There are some reasons that we call binary driven hypernova type 1 the first observation of this, after the first observation of this GRB, we go through the data analysis. First of all, if we have redshift, we calculate the isotropic energy, and if isotropic energy is around more than 10 to 52, if the redshift is less than around 1, we can do some spectral data analysis. And if the JEV radiation is observed, if the sorry for this, if the JEV radiation is observed and X-ray afterglow and all of this observation, we can conclude that this GRB can be binary driven hypernova of type 1, which in the following I will present more detail about this data analysis. As you can see, this GRB 180720b has different episodes that we have recognized. I will explain more. It has many good observation of the different satellite like Fermi GBM, like optical satellite, Swift XRT, Swift BAT, and all this accumulative observation will tell us that this GRB can be a good candidate to study our model that can be proved by this observation. Next slide, please. Okay, what is binary driven hypernova in general? In general, we have a binary which a carbon oxygen core undergoes a supernova explosion, and as a remnant there is a new neutron star and there is a binary neutron star. If the binary period is around 5 minutes and less, we will have the hypercritical accretion on the binary neutron star, which black hole can form. This formation of black hole, which almost this justify almost this energy of more than 10 to 52 Earth in the prompt emission, is a sign, has a sign with JEV radiation, which can tell us this GRB can be a binary driven hypernova of type 1. And as you can see, there are 3 pillars of this model. One is supernova, and it's the remnant expansion of its remnant. Second is new neutron star that has been created just after the supernova explosion. And the third is the new is the companion neutron star. This model of binary driven hypernova has been developed first by Rueda Ruffini and in 2012, and later on by many analytic and numerical stimulation of our group, Becerra et al. And other people of the group, which have developed this model during these years, like 10 years, 12 years. And as you can see, there are some other simulation which has been done in the Los Alamos laboratory with the help of Chris Schreier and the collaborator, that has shown more detail of this model. Next slide, please. Okay, this interaction of the supernova with new neutron star and with the neutron star, companion neutron star, originates different episodes that can be observed in the observational data from the satellites. For example, accretion onto the fallback accretion onto the new neutron star, fallback accretion of supernova ejecta onto the neutron star gives rise to spin of the new neutron star and some radiation that we call as new neutron star rise. It can give rise to the synchrotron radiation, leading to the X-ray, optical, and radio afterglow by synchrotron radiation. And on the other hand, there is accretion of the supernova ejecta onto the companion neutron star, which create a black hole, which has also its own fingerprint, ultra-relativistic prompt emission phase UP. I think you have stopped, Gregory, you have stopped sharing. Hello? Okay. Can you hear me?
Yes.
Yes, excuse me, I had some temporary issue. Yes, is this slide is correct?
The next one. Okay, thank you. So also there are some evidence of this accretion onto the neutron star and black hole formation, which I mainly focus on in this talk about on this side of the binary driven hypernova, which leads to the observation of UP phase, which is ultra relativistic prompt emission phase, the observation of cavity, the observation of early X-ray flare, and the observation of Jeb radiation in these GRBs. As you can see, for GRB 180720b, there are different episodes which the ultra-relativistic prompt emission phase is characterized by its thermal component. The new sunrise is characterized by its cutoff power law. The cavity also cutoff power law, and the early X-ray flares by their mildly relativistic nature, which are characterized also by the observational thermal component. Next slide, please. Okay, on this talk, I mainly, because if I want to explain all the details, it needs lots of time. I only focus on the UP phase of this GRB, which, as you can see, it's in shadow in gray, episode 1 and 3, and the overlapping of this episode by new neutron star rise. I don't go into the detail, but under some circumstances of binary features, like the binary period, binary distance, these two can overlap. But mainly here, I focus on the UP phase and the origin of it, how it can be explained, how and which astrophysical phenomena will explain this. Next slide, please. In the data, when we want to find the UP phase, we search for the thermal component in the prompt emission. And in this GRB, the thermal component is evidence around from 4 seconds in the rest frame till 11 seconds. So it covers almost half of the prompt emission, this thermal component. And when we do the time result data analysis, also we can find in the smaller time intervals during this time integrated from this time of 4 to 11, it can be found this thermal component, which is divided into 2 slices, 4 slices, even 16 slices. Still, we can find this thermal component, and we explain why we can see all these thermal components, these detailed thermal components during this phase by mechanism that we proposed here. Next slide, please. Okay, next. The idea in the binary driven hypernova is like this. We have accretion onto the companion neutron star. Neutron star itself has magnetic field, then the accretion around it will amplify the magnetic field. So at the end, there are also some simulation by Rezzolla, by Wilson and other collaborators that this almost can be approximated with the final outcome with a black hole and the magnetic field which is in parallel and aligned with the rotation axis, almost aligned with the rotation axis. So this configuration, the mathematics is still is not well known, and it needs fully numerical solution, but with a very good approximation we can use some mathematical solution that have already exist in the literature. Next slide, please. Okay, the idea was that we have this black hole, we have the parallel, almost aligned magnetic field with the rotation axis. So we have this solution in the literature, the classic solution of Wald-Papapetro, that when we have Kerr metric rotating inside the magnetic field, we will have a configuration that we call it Wald solution, Wald-Papapetro solution, that the electromagnetic field after some calculation can be written as the right part, column number 3, that there are different components of electromagnetic field. And this electromagnetic field in this configuration have many attractive features, which I show, and why this solution can be applied to the physical condition that we are looking. Next slide, please. Okay, the idea of the mathematical idea behind this was first developed by Papapetro, which showed that the killing vector of each space-time can be considered as the killing vector can generate the solution of Maxwell equation, which straightforwardly he shows this in the case of Kerr metric, 2 time-like and actual killing vector can generate this Maxwell equations. And finally Wald used this solution and generated his solution, which is known currently, we call it Wald-Papapetro solution. Next slide, please. Okay, this solution has some attractive features, that this Maxwell invariant E dot B is not 0. So this shows that we cannot find an observer that the electric field can be vanished. So this is very important for having particle to be accelerated in this situation, for having some other attractive work that have been done 1975 by Ruffini and Damort, showing that when we have non-vanishing electric field, this E dot B not equal to 0, we can establish the Schwinger pair production. That moment they showed it can be the base for this huge amount of energy of 10 to 54 of the 10 to 54 erg of the energy that is released during the prompt emission of the GRBs. That moment they considered Kerr-Newman metric, but later in this work and other work we show that Kerr-Newman metric in that concept that they developed cannot be exist, but all the configuration is the same. And instead of having a largely charged Kerr-Newman metric, we have this discharge of Wald solution. We have this concept of effective charge, that is, let's say, system is charged without charge. So it's not actually, it shows that also charged structure in the nature cannot exist, this new configuration. Although we can use it, this discharge effect shows that GRB, if we want to say GRB is the outcome of discharging the charged black holes. Also, another good aspect is that charged particle can be accelerated, so ultra high energy cosmic rays can be explained partially with this configuration. Also, synchrotron radiation of the around this configuration can be studied. Next slide, please. Okay, what is the idea of having vacuum polarization around the black hole? As I said, this idea was developed by Ruffini Damour first to explain the huge amount of energy that is released around the black hole, that is released in GRBs. The idea was that around the black hole, that moment Kerr-Newman black hole, there are a region that the electromagnetic field is overcritical. Then we have this vacuum pair production, and vacuum pair production later on by Ruffini, Wilson, Xu, and other collaborators, they showed that this vacuum pair production, because of its high internal energy, it makes a huge explosion. That's this explosion can be considered as a GRB, or that moment PGRB. But finally, in the whole picture, we can consider this is the real GRB that we are always looking for. So the high internal energy of E plus E minus plasma makes it expand with highly relativistic velocities that expand till the moment of transparency, and at the transparency point around that moment, I think around 10 to 12 centimeter away from the black hole, we can see this thermal component and other component because of the kinetic energy of the expanding shells. So the whole idea is this: we have an optical thick E plus E minus plasma. Then because of high internal energy, it expands, and at the transparency point, we have a thermal radiation and the other radiation because of the high kinetic energy, which has 90% of total energy of the system, and mostly only 10% is thermal component. So most energy is in the kinetic energy, which can be converted to other like synchrotron or other kind of radiation that we can see. So the next slide, please. But in the new configuration that we use the Wald-Papa-Petro solution, since E dot B is not zero, so this guarantees that we can have the vacuum polarization, and the expansion of these shells was developed by the first idea, as I told you, by Damour Ruffini, 1975, and the expansion of these shells by Ruffini, Salmonson, Wilson, and Xue. And after that, with people of our group, was developed this idea that this expansion can explain this this thermal component that we see during the during the prompt emission phase. Next slide, please. And if you want to write some formalism for the calculating the energy and how these shells are expanding, we have the electromagnetic field configuration of this inner engine. This inner engine, when I say inner engine, I mean this magnetic field, this black hole and low density plasma around. We have this electromagnetic field configuration of the inner engine. Then in analogy with Kerr-Newman, we can introduce this effective charge to mass ratio, which effective charge is 2B0J. So the the interaction of the magnetic field with the rotation of Kerr black hole will produce this produce this effective charge. It's not production, but I cannot find the right word. It's this effective charge. In analogy with this, we can define the radius and energy of this region that field is overcritical, and this region first by Ruffini and the collaborator was called the other region. In the case of Ryzen or some, it was the other sphere, and in the case of Kerr-Newman, it was the other torus. And in this case, since it has a bit strange shape, we simply call it the other region. It has a width, it has an energy. So based on this energy and width, we can calculate the expansion, the velocity at the transparency, the temperature, and all the parameters that we need. Next slide, please. And if I want to give you a simple explanation how we calculate this, we have the energy in the observer frame. We do this transformation. Then we need to have the transparency condition to avoid this compactness problem. And using and I forgot to say that there are some baryons also around these shells. So using the conservation of energy, the total kinetic energy and internal energy, finally we can reach the final formulation that at the transparency point we can calculate the radius of transparency, the gamma factor, the baryon loads, only by having some configuration from our inner engine theory, and some observation like temperature and like the energy that we can define and find it by the inner engine that we have introduced. Next slide, please. Okay, this is the whole picture. This is the whole picture that these shells, that there are many shells, expanding shells. The only thing that we need to calculate the transparency features, the transparency values, is the observational temperature, is the width of each shell, and is the ratio of the thermal component to the total energy, and for sure the isotropic energy of each shell. And after having this, we can calculate the gamma factor and other things. The next slide, please. Using our time resolve analysis, we have found, thanks to precise work of Liang Li, we have found this time resolve spectral analysis that can, with high precision, till the quality of data allow us, we can find the thermal component, total energy, the ratio, and all the necessary conditions that are needed to determine the inner engine's parameter, and finally the transparency condition. Next slide, please. And as you can see, there are some details of the data analysis that we need to consider if the thermal component we find is significant or not. We need to check many models to be sure that this thermal component, which is vital for our model, is true or not, which we have checked. All of them are significant, statistically significant, and the ratio of the black body to the total ratio, as you can see, it has the self-similar behavior. Almost the ratio is 0.4, like 4% of energy, roughly speaking, is the thermal component, and the total energy we have the timing and the temperature and the E cut of each time interval. we use this parameter to put together with the inner engine theory that we have done. And finally, next slide, please. We can find this a result that this is like a lower limit of this solution. I don't go into the detail to find the upper limit, but the lower limit has been found by one extra condition, that during the UP phase, electric field, electromagnetic field is overcritical. So at the moment that electric field, the UP phase is done, is over, electric field is undercritical. So this is the that's why I call it a lower limit of the parameters. And as you can see, the E over E critical is around 1.2, and at the end of the UP is 1, which shows that after that is not critical anymore. UP phase is over. Energy is around 10 to 45. The width of each shell is around 10 to 5 centimeter. And the gamma is around 50. And the radius of transparency in this case is around 10 centimeter. If we consider bigger electromagnetic field, that only a good high resolution data will allow us to tell what is the electromagnetic field. These numbers, for instance, for gamma can go to 100, 200, and the radius is around 10 to 13 centimeter. So this is up to the high quality of data that we can put constraint on the parameters of the transparency. Next slide, please. Okay, and I would like to, my presentation is over. I would like to say again, happy birthday to Professor Ruffini, that I have learned many things from him. Maybe some of the good things that I have learned is that to never give up, always be a good fighter, and always be creative. That's these things have helped me a lot during my career to establish high quality research. And the next slide is our dinner, our New Year dinner with Professor Ruffini, Wang Yu, Professor Kerr, and myself in Pescara, that we celebrated New Year with them. And I think it's also Professor Kerr's birthday. Also, I take the opportunity to say happy birthday to him also. Thank you so much.
Okay, Rahim, thank you very much for your talk. Maybe we can have any question, short question, please. If no question, we thank you once again, and we can move to the last speaker of today, is Professor Pisin Chen. We can hear you. Maybe Sin, hello. Can you please? We cannot hear you, however.
Can you hear me now?
Yes, yes. Now we can hear you.
Very good. Yes,
please,
I just turned on my speaker.
Yes.
So,
can you please share the screen? Okay, very good. We can see it.
Can you see it?
Yes, yes. Please go on.
Okay, very good. Yeah, so may I start?
Yes, yes, please.
Okay, this is a very happy occasion, and I appreciate the opportunity to report to you actually a work which is not exactly new. It's about already seven years ago that Remo and I co-published. This is related to gamma ray burst, but not the theory of gamma ray burst itself, but something to do with bioevolution. and I hope I can help to provide a different spin of what of Remo's very colorful and widespread interests and contributions to science. And if you allow me, I would like to show a few photos that dates back to 2009, when Remo made a special trip to Taipei, and he and I signed a collaboration MOU between ICRANET and Lake Casbah. This was in October 30th, and the several photos show our signing, and and Remo's given a colloquium, and then a nice dinner at the top of Taipei 101. So that was the beginning of this MOU. So then years later, and as many of you have also participated in one of the Marcel Grossman conference back to Rome, and we had a wonderful sightseeing, a trip to Palazzo Colonna. And so here I'm happy to have a nice photo together with Remo. This is another shot with Gerardus Hooft and Hagen Kleintner of Free University of Berlin inside the same palace. This was, I think many of us have wonderful memories of the banquet that evening, but I particularly like to give my memory to a wonderful lady, Mrs. Anna-Marie Kleiner, who sadly has passed away. And this is Truft and his wife. So this was quite memorable. And in one of those, one of the days during the Marcel Grossman meeting, we had, some of us had a visit to the Bessel Foundation. Einstein's, one of the best friends of Einstein's, Michel Bessel, his family's property, and now a foundation. So this was a photo taken together with Sam Ting and Francis Everett, as well as other colleagues. And the reason of showing those was that inside this Bessel Foundation, Remo and I signed the renewal of ICRANET Le Casbah MOU. I'm extremely pleased and honored to continue the collaborations between the two institutes. And shake hands. So now let's back to business. So the point of this talk was to introduce to you, if you did not know before, the idea of GRB-induced bioevolution. And many of you perhaps know about this, what's called Cambrian explosion, where it happened roughly 540 million years ago. The evidence in the fossil record shows that all major phyla were established in the transition from late Precambrian to early Cambrian time. And here, this diagram shows 9 major phyla families that appeared in a rather brief time in terms of the Earth geology, within 10 million years or something, and they just suddenly all emerged. And these, it was the all the major phyla until now. So that's kind of a mystery. And here, just another another figure that I wrapped down to share with you what these major phyla are like. And So that's not our main point. So let me also just say, one of which, this kind of animal by the name Opabinia, it made the largest single contribution to modern interest to this Cambrian explosion because of their fossils. This is called Dickinsoniana costata. This has this really interesting, gilded appearance. And this is also another example of the Cambrian fossils. And here's another one. This is called Marella. This is a specimen illustrates how clear and detailed the fossils are from what's called the Burgess shale lagostate. Lagostate means in geology, this is the terminology in geology, indicates the extreme rich of fossils. And so this is one that, and Burgess shale is in Canada. And this actually was one of the big discoveries on about the Cambrian explosion. Now, so a quick small summary. This, the origin of life and has this quantum jump, if you like to say, that happens at around 540 to 530 million years. So it's by the name Cambrian explosion. Many of you might have read this famous treatise by Charles Darwin, History Making, about the origin of species by natural selection, published in 1859, that revolutionized our human thoughts and our understanding about ourselves and where we came from, etc. However, in the book, he has this very famous statement. He said, and I quote, Cambrian explosion is one of the main objection. Just a second, let me move. The main Cambrian explosion is one of the main objections that could be made against the theory of evolution by natural selection, against his own theory. And he particularly mentioned because it appears that, so let me again quote what he was saying. No, this is not exactly what he said, but let me also quote this statement here. Those observations on the Cambrian explosions were probably Darwin's single most greatest observation during his entire career as a paleontologist. I believe this was stated by another very well-known paleontologist. So just a second. So this is a big thing. Here. So it's taken from the book, The Monkey Businesses, written by Eldridge, published in 1982, 40 years ago, in which he says, the Cambrian period, thought to have started 540 million years ago, is a huge evolutionary enigma. Supposedly, nothing but blue-green algae and bacteria lived for billions of years, and then in a geologic instant, all of the major types of animals sprung into existence. This has been called the Big Bang of biology. No real progress has been made by evolutionists since Darwin's day, and the Cambrian evolutionary explosion is still shrouded in mystery. And this was written in 1982, 40 years ago, but I think it's safe to say in the 40 years since, there was no clear solution. All right, so as physicists, we enjoy challenges. So this is how Remo and I started looking into this. Now, quoting from this paper in Science by Smith and Harper, in which they say causes of Cambrian explosion can be classified in three categories. One, developmental, genetic. Two, ecologic. And three, abiotic, environmental. So they were thinking how to explain this. And so that's experts' opinion. Now, just have a little sense of how the Earth was like. So in the Cambrian era, the Earth was like this. It's mostly water, okay? And especially if there's a huge ocean with some small kind of lands. And then there are bigger ones, Gondwana and so on, but you know, these the ancient Africa, etc. So this is how the Earth looked like. And so the the same Smith and then Harper in the article, they look into the interconnected causes of those three categories that they listed: Earth system, developmental, ecological processes. They have hypothesized as isolated singular causes of the major diversification of marine taxa early in the Cambrian. So this is a kind of a busy, juxtaposition here. Now, many of us physicists have heard, I hope, because it was contributed by us physicists, but this is regarding mass extinctions of the species on Earth. And there were 5 in our history, and this is called Big Five. The Big Five mass extinctions in our quote-unquote recent history, past 500 million years. Now, let me just, so here, the way to appreciate this chart is the red one is the rate, the total extinction rate, the extinction, the number of families per million years. So it goes up and down, but then extinction, in a huge rate, shoots up, and then oscillates, another huge extinction, and then oscillates, huge one, and then the last one, which happened around 65 million years ago. And as we are all familiar, dinosaurs die, totally extinct because of that. And actually, mammoth starts to gradually dominate the Earth after that. So how did this happen? The Nobel laureate Luis Alvarez and his son Walter Alvarez, who was a professor of geology at Berkeley, they together proposed this the cause of this the last of the 5th mass extinctions due to the impact of a large asteroid on Earth. Actually, this is being confirmed, I would say, and that the landing point was the Gulf of Mexico. So we are all familiar with that. Now, let me add a comment that, so the blue ones actually is the integrated ones, the accumulated. So shall we say the instantaneous number of families of animal life on Earth. So it's actually increasing. Now, I wish to say that the focus, and there was actually the trigger of what Remo and I started doing, was a suggestion by some was it chemists to about another mass extinction about ozone layer. No, something to do with astrophysical events. But anyways, the main point I wanted to say here is that the focus has been, used to be, more about how things all of a sudden extincted, rather than how things all of a sudden all emerged. Okay, so this is the Big Bang, the big creation is characteristically different from this type of study, extinction. Okay, and so I wish to make that difference. Now, I don't think this is as important, so let me skip. Now, to help me explain how we come to the proposal, I thought it would be interesting, and this is kind of fun, to recognize that our Earth atmosphere was not the same from the past to now. And one thing remains more or less invariant was nitrogen is almost always dominant, save other than the very early time. By the way, the horizontal scale is not million years anymore. These are billion years, giga years. Okay? So 4.6 giga years before now was pretty much the beginning of Earth. There was a lot of ammonia, methane, and so on. And interestingly, then during a time there were tons of water vapor, carbon dioxide a lot, and oxygen was never there until much more recently, about 1 billion years ago. So this is the situation. And because of that, the emerge of life, there is an interesting interplay between life's influence on Earth's atmosphere and vice versa. And for example, the nitrogen is slightly less than before. Let's see, no, percentage-wise, it's actually increased. Now, this is in log scale. Oxygen increases, carbon dioxide decreases, and monoxide also decreases, etc. Okay, but this is not the main point of my talk. I was just trying to establish a model to do my calculation, to do our calculations. So first, let's post our issue here. So might Cambrian explosion be induced by a nearby gamma ray burst? And what does it mean by nearby? I'll define it later. And the suggestion is that intense gamma rays, after penetrating the atmosphere, would cascade down to the sea level and induce active DNA mutations, which would not, it's an artificial trigger, and which we all know. And in biolaboratories, if you want to research on mutations, you just shine it with X-rays, etc. But anyways, so that's kind of what we're suggesting. And let's begin with Cambrian atmosphere, which can be modeled with this this function. And here n is the density of the air as a function of height, starting from sea level. And one defines the end, the top of the atmosphere at 44 kilometers above sea level. So this function, by the way, is defined only for small h less or equal to big H. And so to the k-1 power, where k is 5.5, and n0 is at the sea level, and that's 5 times 10 to the 19 per centimeter cube. So this is our air. Then, since we consider penetration of photons through the air, so first let's care about photon atom interaction. There are 3 major physical processes, namely photoionization that dominates low energies below 50 keV with such cross section. And second, the Compton scattering. This dominates the medium energy between 50 keV to 50 MeV. And beyond that, the pair production dominates. Here is a chart, but just to let you know that, we know what we're doing, but not very important. So you can check through the elements and find out the, and vertical scale is the photon energy, horizontal scale is the number of atomic number of elements. And since we're worrying about mostly nitrogen, oxygen, so it's at this around here, and energy is typically 100, tens to hundreds of keV up to hundreds of MeV, so it's mostly here. Okay, now so blue means it's the cross section is this is in the unit of 10 to the minus 24 a barn per atom, so this is kind of on the low side. Now so this is the well-known Compton scattering, the Klein-Nishina formula, and the X and X prime are the initial and final photon energy in the units of MeV, and this is differential cross section. The cross section for X at 0.1 is 3.9 barn, and at 100 is 0.1 barn. Now for pair production above 50 MeV, it's more or less just 0.1 bar. So as we will see, the gamma ray burst spectrum would diminish at high energy, while the portion dominated by photoionization cannot survive to the sea level. They do photoionization and they just, essentially lost by penetrating through 44 kilometers of air. Thus, only Compton scattering in the range of X around 0.1, meaning 100 keV to 100 MeV contributes effectively to flux at the sea level. Now, so let's take a look of the gamma ray burst incoming flux. And here we invoke the band function with alpha equals -1 and beta equals -2. And so the incoming flux looks like this, and where X is what's called the break of the spectrum. Typically, the X0 is of the order 1. So that's great. So now we follow Melot et al. To assume that the isotropic equivalent energy release by a GRB is about 5 × 10⁴ watt. Then the flux at distance d away from the Earth is as follows, where F is defined below. Sorry. Yes. Now, how about down to the sea level after penetrating the atmosphere? How much of that is survived? But doing that, I first like to remind everybody that Compton scattering has this very interesting property, which is that the photon number is conserved. So there is always one photon in the initial state and one photon in the final state. So the flux remains the same, from top to the bottom. And so this is absolutely important. Now, so here is some small technicality. There is what is called the forward cone approximation. So we assume that, and this is an approximation. So we assume that Compton scattering with outgoing photon angle theta larger than theta c, and here I say equal to 1, is considered to be totally lost. While inside this forward cone, an averaged outgoing energy can be estimated or calculated as follows. And this is invoked to track the evolution of Compton cascades down to the sea level, what we did. So the GRB final flux is reduced from its initial value entering the Earth by a factor 5 × 10⁻⁵. So that's the result. And so here's a plot. So So horizontal scale is the incoming photon energy in units of MeV, and vertical is the flux. Now, you see, it's kind of a small, quick summary of what I already said. It depends on the incoming photon energy. There's three categories or three regimes: photoionization, Compton scattering, and pair production. And the blue curve on the top is the initial gamma ray flux based on the band function. Now, based on that and tracking through the calculations, one comes to a final GRB flux at the sea level, shown in red color, essentially in the Compton scattering regime from 100 MeV KeVs to 100 MeV or so. Now, now imagine that our photons have arrived at the sea level. What does it do further? Now, the photon will penetrate through either water or soil. These are dense medium, and the mean free path of X-ray photons in water is about 10 centimeters. Now, interacting with the seawater, these X-ray photons would soon cascade into softer photons and electron-positron pairs and deposit their energies to water and to marine organisms. For a GRB event that occurred at a distance of 500 parsec within our galaxy, 500 parsec from the solar system, the photon energy deposition at the sea level is roughly 1,000 rams. So marine organisms living several mean free paths below the surface might survive because the X-rays, soft gamma rays have deposited their energies rather efficiently to the water. Of course, it would heat up the water, but there would be still quite some X-rays, soft gamma rays, still penetrate down to, let's say, 30 centimeters, 40 centimeters below water. And primordial animals, very, initial life beings, they typically live in the swamp with waters, mush and so on. And so there will be some lucky ones. Of course, a lot at that instant were quite much closer to the water surface. I think they would just instantly die because of this impact of the photons. But there can be some shallowly underwater or shallowly just right under a rock or some small layer of soil can survive, but it was forced to induce DNA mutations. This let me also skip. So let me end by asking whether there is possible evidence of our claim. Now, gamma ray induced gamma rays, if indeed, well, not even if, they must penetrate, because physics shows us when they penetrate down, they don't just do the biomutations, but they will also induce transmutation of the so-called giant resonance region of photonuclear reactions, which corresponds to photon energies about 15 to 30 MeV, and the cross sections are large, and nuclear transmutations can be induced effectively. The following is a list of elements in the giant resonance region that undergo nuclear transmutations, some of which may have half-life which is long enough, let's say 100 million years or a couple 100 million years. Then there should be still isotopes surviving till now, and from some geological layers that corresponds to the Cambrian era. So this can be a good evidence for that. There's also the possibility, if indeed a GRB was exploded about 500 picoparsec away, then within that sphere, and all the exoplanets within that sphere from our other, from our solar, would subject to a similar stimulation of DNA mutation, and that should accelerate also the bioevolution if it is has an atmosphere similar to ours. For example, this is not exoplanet, but our own solar system, Mars, has an atmosphere, and many by now believe that there may be some primeval life beings there, and if we have a chance going, Mars may do some investigations and see if that is coincident with our Cambrian explosion. So these are all possible, and also there are also unprotected primitive microscopic organisms carried by interstellar rocks, which may turn sterile after being exposed by this same GRB. And however, such seeds of panspermia would evade GRB destructions if it has migrated and colonized rate is faster than the GRB event rate within a volume of destruction. So this is some possible other evidences. Oh, one thing I forgot to say was, I should have, but we can check, and based on our accumulated data on GRBs, you can estimate the frequency of GRB explosions per galaxy I checked, and to have such a nearby GRB happening in our Milky Way is roughly 10 kiloparsec, many parsec. So you calculate, you estimate, and it does not happen so frequently. It can be easily billion, 1 billion years or even longer. So that is a kind of a side comment I'd like to make. Sorry that I didn't prepare. I forgot how many billion years per event but it is for sure not as frequent as million years. Otherwise, this theory will fail. So a quick summary. So one long-standing mystery in bioevolution since Darwin's time is the origin of the Cambrian explosion that happened around 540 million years ago, where an extremely rapid increase of species occurred within, as I said, 10 million years, which is short in the center of geological evolution. Now, a nearby GRB event, 500 parsecs away, which should occur. Here it was what I thought I've missed. So thank you. So I'm glad that I've indeed put it down here. So I estimated, and it should occur about only once per 5 giga years. So this might trigger the Cambrian explosion. And due to a relatively lower cross-section and the conservation of photon number in Compton scatterings, a substantial fraction of the GRB photons can reach the sea level, and then it would induce DNA mutations in organisms protected by shallow layers of water or soil. So thus the expediting the biodiversification. So that's the thesis there, that's the claim. And I am dearly wishing that geologists would be able to help and discover some long half-life, isotopes on Earth or with some specimens from Mars. So happy 80th birthday, Remo. I'm not sure, I don't see Remo's face, but happy birthday, Remo. Thank you very much.
Okay, thank you very much, Professor Pisinchen. We enjoyed your talk. Do we have any short questions, please, from the audience?
Yes, we have one here from Professor Piran.
Okay.
Very nice talk, but I have a question about what do you mean by a GRB? Because GRBs vary in intensity by about 4 or 5 orders of magnitude. And correspondingly, they have different rates. The more luminous ones are much more rare than the less luminous ones. So when you say a GRB at 500 parsec, what is the luminosity or actually total energy output flux that you are talking about?
Yeah. So thank you for the question. I think I have mentioned somewhere. Let me search. Oh no.
What is the flux in kilojoules per square meter that you are discussing?
Yeah. Sorry, I was quickly searching for where I had it.
Previous slide, I think here.
Yeah. It's here. Yeah. So I follow Melot et al. To assume that the isotropic equivalence, and so I was assuming that that GRB had an energy release of 5 × 10⁴ watts, and so the flux.
44. So 50. So 10 to this is 10 to the 51. 5 times 10 to the 51.
Right. Right. Now, this was just as a reference because I, without having the information from biologists to know how big a flux of X-ray and gamma rays is sufficient to accomplish the job. So there's an open end on the other side, and so this number I took was just as a reference. Not sure whether that's necessary or not, but so this is some assumptions, and based on that, I was able to at least estimate the flux when arriving on Earth, and then what's the survival down at the sea level. Yeah.
Okay.
No, I have maybe a related comment. If we don't know that, maybe we don't know the lower ends, right? On the, I mean, the lower part of the energy. You know how low this can be. But as you go, as Professor Piran just mentioned, for low energetic GRBs, they are more numerous. So if they are more numerous, that would mean that maybe we could the Earth. We could have more events like this one, but maybe these events didn't happen. So maybe we can put a limit from that side.
Yes. Good point. I got it now. Yeah. Very good point. Yeah. Now, with regard to the importance or relevance of the hardness of the spectrum, this was what I assumed. Now, if it is softer, then since, as I have explained, energy is softer than this, into this area, photoionization is essentially killed all the incoming GRB photons. So it's softening this part, yeah. And as we are familiar with GRB spectra, either long bursts or short bursts, but here I was more thinking in terms of short bursts, and there can be variations for sure. And the missing link here was, I have no data from life scientists as a lower bound on how much flux is required in order to trigger the stimulated mutations.
What's wavelength of the main wavelength of photon which make a job range?
What wavelength? Yeah. Now, typically in the bio laboratories, they use X-rays, hard X-rays. I feel that it was mainly due to the fact that
KeV, a soft X-ray, KeV,
more than KeV, 10 KeV type of, KeV, 10 KeV around. Now, KeVs, thank you. And so, but I suspect it is because, harder gamma ray things like MeV or hundreds of KeV is not easy to prepare in the ordinary life science labs. I don't know if one can find data about mutations based on those energies of photons, which I don't know.
Okay, I think at this point we should maybe keep going with the program if everybody agrees. Thank you, Professor Chen, once again for your wonderful talk. It's of course very interesting, connected to all the exoplanet activities in the recent years. And we have actually stopped the morning session, and now the new session starts where people can congratulate Professor Ruffini with his birthday. They can just deliver occasional greetings, speeches, and therefore we formally close the morning session, but the connection will be open, and there is a program on the Indico website, so everybody can join and listen for this session. The next science session will start at 3 o'clock Italian time, 3 p.m. With the talk of Klaus Lammerzahl, I think, right? So please refer to the program on the Indico website of the meeting. Okay, thank you very much for participating.
Thank you.
See you.
Bye. Bye.
Good afternoon. Is here someone hearing me? Young, how are you? Well, my duty is to do some sharing during the lunch break. Hopefully, we will do also the lunch break. But is there Saken Toktarbay, Joan Rafelski, Gren Matthews, and Stefano Ansoldi? So if you are there connected, please show up and start your contribution. And the secretariat here is telling me that Professor Ruffini is now in the hospital of Nice, and I heard his voice, so he's able to speak. Then we hope he will recover soon. But as usual, the meeting must go on. Grant Matthew, are you ready?
Yeah, I'm here. Okay. I don't know where everyone else is, but okay. Let's see, I'll share my screen. Sorry to hear about Remo's trouble.
It's a news for us as well. We are here in Pescara. So I suppose all the gap of lunch break is filled by your contribution, then I think 20 minutes for your contribution. Is it good?
Yeah, 20 minutes is more than what I need.
Perfect.
You can see my screen okay?
The other speaker, please write me through chat in order to organize your intervention. So please go on, Grant. Thanks.
Yes, well, it's an honor to be asked to speak here. Here at this birthday party for Remo. I just wanted to say I've enjoyed my friendship and collaboration with Remo, particularly in recent years. I just wanted to say he's the most hardworking, articulate, creative, and demanding collaborator I've ever had. So it's a joy to work with him. And we first got together through our mutual friendship with the late Jim Wilson. And Jim was always enthusiastic and proud of his collaboration and friendship with Remo. Remo and I have worked on a few papers in recent years, many hours discussing the afterglow, X-ray afterglow of gamma ray bursts. That's not what I'm talking about today, but let me say that talk inspired what I did want to talk about today, which is a little project I've been working on with my graduate student, which convinced me the need to go back and restudy the binary neutron star coalescence, and in discussion with Remo is how it relates to the, hyper-driven, binary-driven hypernovae. But so what I want to talk about today is actually a typo in the program. It's binary neutron star mergers, not merges, and the quark matter equation of state. Let me say this is mainly the work of my graduate student, Atul Kadia, who is just defending his thesis this month. And he's done good work. Jim Wilson and I, and we worked some with Remo on this, developed a code for binary neutron stars years ago, but the technology is much better now with the Einstein toolkit. So now we run fully relativistic simulations of the merger based on the Baumgart-Shapiro, Shibata, Nakamura method of normalizing or regularizing the equations of motion. There's a good code called the REAN that gives us the initial conditions as we start out. Just details the relativistic hydro has mesh refinement built in, and we extract the gravity waves by the Newman-Penrose formalism. So it's a much better platform than the calculations Jim and I did some years ago. So the premise of this work is that once you form the hyperneutron star in a binary neutron star merger, as it collapses down to a black hole, in essence, you'll see all phases of matter, most of which would occur in inside the horizon, but there's one that you can sample on the outside of the horizon, which is the transition from hadronic matter to quark matter. It barely makes itself known, and but it turns out it gives a very unique signal, which I will get to, which is why I'm very excited about this work. Now, there have been previous studies on binary neutron stars and the formation of quark matter. Most of those deal with except for this recent one by Huang 2022, who did work very similar to what we've done. They mostly deal with the first order transition as the hyperneutron star collapses into a black hole. If it encounters a first order transition to quark matter, then the pressure support of the star is diminished. The star increases the pressure, that energy just goes into forming one phase into another. So in fact, the collapse to a black hole is hastened. But there's another possibility. This is a conjecture from Schaefer some years ago, but it illustrates the point. Once you cross over the density into quark matter, there's a potentially complicated phase diagram. You could have 2-color superconductivity, 3-color superconductivity, flavor lock state with a kaon condensate or not. This is a speculation of a kind of a crystalline phase when you have mixed amounts of strange matter. And it's in a non-perturbative regime of QCD. So what I want to propose is that one might be able to probe this complicated phase diagram, and probably the only place in nature, because it's very hard to get to it in heavy ion collisions. Maybe the only place in nature you can probe this is in the last moments of the formation of a hyperneutron star in binary neutron star mergers. And that's sort of a sketch of kind of how the density evolves in one of our simulations, a central density as you head towards the black hole. So what happens as the system collapses to form this quark gluon plasma? I did calculations in the past where we just assumed an MIT bag model, but it's not, the material is not asymptotically free. That doesn't come in until very, very high density. So you have to take into account that there's non-perturbative effects that I already mentioned. There's quark anti-quark pairing that contributes to the quark constituent masses and the chiral symmetry breaking, which was on that plot. There's also quark-quark pairing that gives the superconductivity. The framework that we chose to do this work is based on the quark-hadron crossover transition of Gordon Boehm et al. In 2019. There's a newer version which we're running now, the QHC 21, but what I'm talking about today is the 2019. The idea is, as I mentioned, that the transition from hadronic matter to quark matter does not have to be a first order transition. We know from lattice gauge theory that the transition at low density, high temperature is in fact a crossover transition, but the transition at finite density may be weakly first order or first order, as others have assumed, or a simple crossover transition. So let me just explain a little bit about this equation of state. In the actual QHC, the hadronic matter is treated in the APR equation of state, and then it was extended a little. In the calculations I'm going to show today, we used a variety of hadronic equations of state. A typical soft one is what's called the SLY4 equation of state. And then we also use an example of a stiff equation of state for comparison. But when we reach the quark hadron regime, once we get 4 or 5 times the density of nuclear matter, the transition is treated as a smooth crossover, which is easier to do numerically. Now, the quark matter is treated in this Nambu, Jonah, Lacino effective Lagrangian, which I just write it out here. Besides a normal Dirac-like term, there are these 4 quark and 6 quark Lagrangians, and that's where the interesting physics is. There are 3 coupling constants if we just look at the 4 quark term. There's a coupling constant for a pseudoscalar piece that's just normalized, can be normalized. But the ones of interest here there's this diquark piece, and that's the one that affects the color superconductivity, and a vector coupling, and that's actually needed to give a repulsive interaction to make sure you can have a heavy neutron star. So this, for example, was a figure from the Bain paper that shows various parameterizations in terms of this vector coupling and the quark pairing. And this series of equations of states going from A to D corresponds to the set of a set that is consistent with the constraints and maintains causality. But there's something interesting about this. As you go from A to D, basically the pressure response to material is going up. And it turns out the transition that's going to occur as the hyperneutron star is still outside the horizon, we can still see what's going on, actually is sensitive to which one of these equations of state occurs. So I've got some movies now just to illustrate this. So what's the effect of switching from a purely hadronic equation of state? So I'm going to show two movies, start out with identical initial conditions. And the one on the right has the QHCB, which is just a moderate amount of pairing strength. But the thing to note is that the normal matter equation of state collapses to a black hole right away, whereas the QHC, the quark hadron crossover transition, actually endures for code cycles about more than 1,000. So it's about almost 10 milliseconds longer duration in this ring down phase after this hyperneutron star forms. Next question is, what happens if you increase the coupling strength? That is, go through this series of A, B, C, D. Each one has a higher pressure as you enter into this crossover transition. So this again is two calculations, both of which head towards a quark hadron phase and enter this crossover transition. The one on the left is a little weaker, one on the right has a little higher pressure. They both start out initial conditions. The timing's a little off in the movie, but as you'll see, it makes a big difference as that pressure is increased. The simulation on the right, notice that about 7,000 code cycles, the lower pressure one collapsed already to a black hole. You'll see the one on the right actually continues on many milliseconds later. And in fact, we get to the end of the simulation, it has just barely begun to form a black hole. So this is a illustration of what we just looked at. As I mentioned earlier, we use a Newman-Penrose method to extract the gravitational radiation. So we want to see what this looks like in time. The two simulations down here, these are normal, just hadronic equations of state going through their evolution. This is the start of the calculation. The merger happens here. And you can see for normal hadronic equation of state, after about 10 milliseconds, this ring down ceases and you form the black hole. But as you go on to the crossover into the quark matter phase, as you increase the pressure, this ring down endures much longer. Now, this is about a 3 kilohertz signal. So the question is then, is this something that can be seen? And note, particularly, for example, this example, the QAC19C actually lasts for like 50 milliseconds. In fact, if we went to the QAC19D, it never collapsed as long as we could run the simulation. It maintains a stable hyperneutron star. Okay, so the way to look at this, what a laser gravity wave interferometer would see is this spectral density, which Fourier transform of those gravity waves that we mentioned. This first peak it actually corresponds to the chirp. It's called F max, but the one that we're very interested in is this ringdown peak that occurs at about 3 kilohertz. We call it F peak, some people call it F2. And what you see in this diagram is we go from a normal hadronic equation state up through the quark matter crossover transition. The strength of this peak gets much higher, and that's because of this long duration during the ring down. Now, for illustration, this is the sensitivity of the Einstein telescope. So there is a chance to actually look at this, dial in, and see if this secondary peak at 3 kilohertz stands up way above the noise. Now, as a caveat, I have to say there are other equations of state that have the right properties that could cause this duration. So the unique identifier that could be used to decide if you have this crossover transition to quark matter is a number of papers have voiced this. There's a universality relation basically between those peaks, and in this graph here, it's the tidal polarizability. Okay, so this is the first peak up to the chirp, and in that case, all of our simulations up to the chirp, you'll still be in the normal hadronic equation state. So it follows along, you know, the SLY looks like this, our equation state look like that. Okay, where the interesting physics is, if you look at what we call F peak, which is that ring down frequency, once the hyperneutron star forms, a soft equation of state is way up here. A stiff equation of state is way down there at a lower frequency. You get, if you have this crossover transition, what we find is there's a unique range in this universality relation that causes these equations of state to fall kind of halfway between a stiff equation of state and a soft equation of state. And it's because the equation of state starts out soft, say, and then it stiffens up as it forms this crossover transition. So I already mentioned this, but just as an advertisement, you know, current sensitivities are up here at this 3 kilohertz range. You couldn't see it, but as we saw on the other slide, the next generation cosmic explorer Einstein telescope might have a chance to see it. Now, that's really all I wanted to say about this today. So I'll just summarize my 2 conclusions that I hope I've at least given plausibility to. One is that this, a weakly, that's a typo, it's not first order. It's a crossover transition provides an opportunity to explore this regime of non-perturbative QCD. Now, whether one can uniquely identify it, we're in a referee fight about that, but I do think that there's evidence for this. And this 3 kilohertz this 3 kilohertz signal, this F2, this F peak, is the actual probe, we believe, of this non-perturbative QCD. And with that, I'll stop. Thank you. And happy birthday to Remo.
Thank you, Grant. I have seen, thank you also on behalf of Remo for the wishes that he will see after the recovery. We are recording everything. I have seen Johan Rafelski connected.
Yes, I am here.
Okay, please go ahead.
Okay.
Have a nice talk. 15 minutes around 20.
Yeah. You want me to share? Okay, I will share. Here we go. So I really make here a short cameo appearance, as one calls it, to honor Remo, with whom I do share not only our passion for relativity and astrophysics and cosmology, but also, as it turns out, birthday. He's born on May 17th, and I am actually born on May 19th, and I am actually at a conference in my honor, a small conference, which my friends organized 2 years late for my 70th birthday. So that's the reason I cannot join you in person, and I apologize, Remo. And I wanted to give in this short presentation a few snapshots of our ongoing research, which basically addresses a topic related to the last lecture, and that makes it a very good place, so namely how matter was created in the universe and how it evolves. Some snapshots of our interest. So I remind everybody that some 20 to 30 microseconds into the lifespan of the universe, the coagulum plasma hadronized and made all the matter which we know, which actually was at the initial moments matter and antimatter, but as we all understand it, a annihilation phase followed. So here we did a couple of years ago, Jeremy Birrell and I decided that it would be very instructive for the world to see how this is a pie diagram. Different components of energy in the universe are combined here. And you see coagulum plasma was initially dominant. And then as matter and antimatter annihilated, we have emergence of neutrinos and photons. You see in red the photons and in green the neutrinos. And as different mesons and baryon, antibaryon disappear, there's a short period of what I would call photon, neutrino, electron, positron plasma in the universe. But electrons, positrons annihilate, and I will show a little more precisely how this happens. And it turns out that, which is, I think, of some significance, that BBN, Big Bang nucleosynthesis, occurs in the midst of a very dense electron, positron plasma. Then for a long period of time, we have a photon neutrino free streaming desert. Nothing much happens in the universe, but as universe dilutes and the energy density gets lower, slowly we emerge with dark matter and normal matter. And then recombination occurs. We have observational cosmology, which happens here. The part of neutrinos and photons become very small. And finally, just yesterday, literally in the history of universe, dark energy becomes important. And that's where we are today. Dark energy is dominant, but as you can see, it's almost hard to recognize on this logarithmic time, temperature and time scale that this just happened yesterday. So matter so I will show a couple of snapshots of our research. And the first snapshot is interest in BBN. in midst of electron-positron plasma. So this just a short demonstration how it works. We already quite a while ago recognized that in order to control the conditions in the universe, one has to prescribe a certain baryon content, entropy content, and then with a little bit of theoretical physics, one can show that the electrons and positrons split in the abundance. Electrons are required to keep the universe neutral, but positrons rapidly disappear. This time the temperature goes from left to right. And this happens around 20.4 keV. So we have a Big Bang nucleosynthesis where the number of pairs per baryon is of the order of 10 to 6, 10 to 7 to 10 to, I mean, it's enormous. It's a very dense plasma, and very little attention has been paid to this detail. So I think this has been kind of this recognized slowly in the community of nuclear physicists that the previous efforts to study BBN and vacuum were really preliminary, if I may call it that way, and plasma environment will play a very important role. So we are a little bit into that and working on in this direction. Another snapshot of what we're doing is we, as everybody knows, there's a relic magnetic field in interstellar space. There's something disquieting, you know, where what is the origin of this magnetic field, but this is perhaps for another time. I just want to point out that standard scaling with expansion of universe makes the in the field of my expertise, which is really traditional quark-gluon plasma and prior epoch, these magnetic fields become as strong or stronger than what we know from magnetars and from strong field QED. So we really need to rethink baryosynthesis, create basically the origin of baryon number as being probably related to very strong magnetic field, something which probably needs much more attention than so far has happened. So we are interested in that as well. And as I said, this is just a short appearance to thank Remo for his continued support of all relativistic physics and cosmology and astroparticle physics. And I just show here a small, I selected 2 pictures from some executive committee meeting where I was present, and from the meeting with students. You see here some current speakers, literally, who just spoke, will speak, or chair the session, or organize the meeting. They were much younger, like that picture I think I took like 12 years ago. Remo always on the phone, and students waiting for him to come off the phone. Well, that's a that's standard, I think, of the way things operate. So, yes, happy 80th birthday, Remo. I really am happy that that you enjoy a good time, and that you can, but you will have many returns, I hope, and that in the years to come, we still will meet and collaborate and develop further our understanding of a relativistic astro world. So thank you very much for being there for everybody in relativistic astrophysics. Thank you. Bye-bye. That's all I want to say. I think I finished. I'm having stop share. If there are any questions, I'll be happy to answer them.
I have just one question. Could you elaborate a little bit more of how the primordial magnetic field could induce the baryogenesis?
Okay, sure. I mean, we As everybody knows, the CP, I mean, there's not enough CP violation in the early universe to explain baryogenesis today, and we are working. One of our projects is actually to show that magnetic fields impact the degree of CP violation of the early universe. I don't want to tell more until we archive the paper. I don't want to make further advertisement how it is.
Okay, I understand.
But then it's very clear that that there is a connection which we are exploiting.
Thanks.
Thank you, Professor Rafaelsky, for your contribution to the birthday, 80th birthday of Remo Ruffini. I am asking if there is the other two speakers, Toktarbay and Ansoldi. If not, I can take these few minutes to present also my regards to Remo Ruffini. We are doing here in Pescara a parallel meeting dedicated to the students of high school, because Remo Ruffini studied here in Pescara the high school, the classical lyceum. He was always linked to this city, as you know, because there is the center of ICRANET here. And but since the time in which this place where I am was a train station, it was about 25 years ago. It was still the old station of Pescara. And now, you know, it is a wonderful research center and coordinating center for all the center of relativistic astrophysics in the world. I want to share the topic of the works that we will conduct today and tomorrow with the student of Galileo Galilei Lyceum of Pescara. If you can see my screen, I am not very sure that, yes, it is written that I'm sharing the screen. If you can see my screen, this is the sunrise of today from Lanciano at 256 meters above sea level at the telescope. You see, there is there is a very complicated phenomenon of multiple rising phases of the sun, because the light of the sun is reflected by some inverting atmosphere, inverting thermal profile atmosphere. There are several of them, let's say in horizontal position, and they are separated by some kilometers one from the other. And so you see the sun rising, but you don't see only one sunrise, but you see many sun rising. This is the project we are conducting with the student of Pescara, the study of the atmospheric refraction using the sun at the horizon, the sun at the horizon of the Adriatic Sea in this case, and from Roma, we observe the sun from the Tyrrhenian Sea, but not from such a high position. Usually we observe from the beach, so these phenomena are not visible. There is only a simple mirage effect. While I am talking, the image is in real time, the video, so you can appreciate the phases of the sunrise. The program of today is also related to the lunar eclipse that was visible on a whole Earth hemisphere. Here we saw the lunar eclipse at its beginning in moon setting. The moon setting I observed was on the Maiella Mount, which is visible from here, even in Pescara. I was in Lanciano doing this observation, and then we will have the contribution of Professor Jai Pasachov of the Williams College in the United States, that will speak us on solar eclipses. The solar and lunar eclipses are always jointed, because when you have a lunar eclipse, it's very easy that the previous or the following new moon will be a solar eclipse as well. And my specialty during these 20 years was the measurement of the solar diameter. Starting from the methods of Dike in Princeton, the same university in which Remo Ruffini collaborated with Professor John Archibald Wheeler. And this is not deformated by the optics. This is exactly the form of the sun today around 5:35 a.m. And also the sea was visible in the back part, in the down part of the video. I don't want to interrupt the video to move to another page, because I think this video is worth to be observed and simply contemplated. We want to do some quantitative study on that video, but it is the result of, let's say, a 2-year approach, even 3 years approach to this observation that are very, very complicated, because the video, here you can see a solar spot, a group of spots here and there. The observation of the sun through the telescope without filters is something very demanding for the camera. And the camera in this case was the camera of a smartphone. Here another group of spots. There are 2 big spots today, 2 big spots groups of on the surface of the sun. And the phenomenon of multiple rising continues. You have seen this part of the sun detaching from the whole body of luminosity, and while the sun is still going up in the sky. Again, another phenomenon. So these are as many images you see. The biggest one is this one, will detach in a few seconds. They correspond to the structure of the atmosphere where the thermal inversion occurs, and they are separated by some kilometers one from the other. Here you have the last detachment and the vision of the sea, of the trembling light of the sea in a Dantesque appearance, or even D'Annunzio, the poet of Pescara, who described making his words, but using the words of Dante about the shaking of the sea, the tremolar della marina in Italian. Dante uses these words in the second canto of Purgatory, when Dante and Virgilio saw for the first time the sunrise. Before seeing the sunrise, they see the horizon, the sea horizon, and sicché di lontano conobbi il tremolar della marina, says Dante, and repeats D'Annunzio in the Pioggia del Pineto. For the sunrise, it's all. For the program of today, let's see if I am able to show to you the parallel meeting of Pescara, where I don't want to shut down the participation. Is here, but I can't go. Okay, this is the parallel meeting of Pescara. So you see the topic of today, and tomorrow I will speak about the solar forcing to climate change. And the mayor of Pescara, Her Excellency Carlo Masci, will give the Mersenne Prize to the students of Pescara and of Rome attending this meeting in person. With this contribution, we wish to Remo Ruffini our warmest regards and congratulations for his brilliant career and his great contribution to science and to the citizenship, especially of Pescara, because bringing here a research center and bringing here continuously researchers is very, very important for Pescara and for Abruzzo, the region in which Pescara is. It's a vision that he had and he shared with me since the very beginning, and I am proud to have been among his collaborators since the birth of this splendid reality of Pescara meeting and coordinating center. So I come back to the role of temporary chairman of this session, and I ask if Stefano Ansoldi or Saken Toktarbay are online. To present their contribution. Otherwise, I transmit to all of you my best regards, and through the chat, the ICRANET web page on this parallel meeting, and tomorrow we will have a jointed session during the awards, the Mersenne Awards that Remo Ruffini has sponsored for this special day of his 80th birthday. I sent through the chat the link, and I do another check on the list of the people present, but I don't see the two other speakers. So I wish you a good lunch for the ones who are in the same time zone, and I conclude my chairmanship in this moment. Goodbye. The meeting will resume at 3 o'clock, so in 45 minutes.